Mars has captivated human imagination for thousands of years, appearing as a bright red wanderer across our night skies. Ancient Babylonians named it after Nergal, their god of war and pestilence, while Roman soldiers looked up and saw their deity of battle watching over them. This single point of crimson light has inspired countless myths, sparked scientific revolutions, and today represents humanity's next great frontier. Let us journey together through the complete story of Mars, from the earliest stargazers to the robots exploring its dusty surface right now. Long before telescopes existed, ancient peoples watched the heavens with naked eyes and curious minds. Among the wandering lights they observed, one stood apart from the rest. A distinctly reddish point of light moved slowly against the backdrop of fixed stars, sometimes appearing to reverse its course in a puzzling dance across the celestial sphere. This was Mars, and its unusual colour and movement made it an object of fascination, fear, and wonder for civilizations around the world. The Babylonians, who developed one of the earliest sophisticated systems of astronomy, tracked Mars with remarkable precision. They called this ruddy wanderer Nergal, naming it after their god of war, fire, and the underworld. Nergal was a fearsome deity associated with death, destruction, and the scorching heat of summer. The Babylonians believed that the movements of celestial bodies directly influenced events on Earth, and so they watched Nergal carefully, recording its positions on clay tablets in cuneiform script. These ancient astronomers noticed that Mars completed its journey through the constellations in roughly 2 Earth years, and they documented its retrograde motion, that strange backward loop it appears to make when Earth overtakes it in their respective orbits around the Sun. To the Babylonians, this erratic behaviour only reinforced the connection between the red planet and the unpredictable nature of war and chaos. In ancient Egypt, Mars was known as Horus the Red, or sometimes simply as the Red One. The Egyptians associated the planet with Horus, the falcon-headed god who represented kingship, the sky, and war. The blood-red colour of Mars reminded them of the fierce battles Horus fought against Set, the god of chaos and disorder. Egyptian astronomers incorporated Mars into their calendar systems and religious observations, tracking its movements across the sky with the same dedication they applied to the Sun, Moon, and other visible planets. The red planet's appearances and disappearances were noted in temple records, and its position relative to certain stars held significance for priests interpreting divine messages. The ancient Greeks initially gave Mars 2 names, reflecting their early confusion about its nature. They called it Pyros, meaning the fiery one, when it appeared as an evening star, and Ares when it shone in the morning sky. Eventually, they recognized that both appearances were the same object and settled on associating it with Ares, their god of war. Unlike the Roman Mars, who was a dignified and respected deity, the Greek Ares was often portrayed as brutal, bloodthirsty, and somewhat crude. He represented the violent and untamed aspects of warfare, the chaos of battle rather than military strategy and honour. The Greeks observed Mars carefully, and their philosophers debated its nature. Some, like Aristotle, believed the planets were perfect crystalline spheres embedded in rotating celestial shells. Others wondered if they might be worlds unto themselves. When Roman civilization rose to prominence, they adopted much of Greek astronomy and mythology, but transformed it according to their own cultural values. Mars became one of the most important gods in the Roman pantheon, second only to Jupiter himself. Unlike the Greek Ares, the Roman Mars was a noble and respected figure, the father of Romulus and Remus, the legendary founders of Rome. He represented not just warfare, but also agriculture, protection of the state, and masculine virtue. Roman soldiers prayed to Mars before battle, and the month of March, when military campaigns traditionally began after winter, was named in his honour. The red planet bearing his name was watched closely by Roman augurs, who believed its position and brightness could foretell the outcomes of wars and the fates of emperors. Far to the east, Chinese astronomers developed their own rich traditions of observing Mars. They called it Yingwo, which translates to sparkling deluder or fire star. This name reflected both the planet's reddish colour and its seemingly unpredictable movements. In Chinese astrology, Mars was associated with fire, summer, and the south. Its appearances and movements were carefully recorded by imperial astronomers who served the emperor by interpreting celestial omens. The Chinese believed that unusual behaviour by Mars, such as particularly bright appearances or close approaches to other planets, could signal disasters like war, drought, or the death of rulers. Chinese records of Mars observations span thousands of years and have proven valuable to modern astronomers studying the planet's orbital history. In ancient India, Mars was known as Mangala, a name still used in Hindi today. Mangala was associated with the god of war and was considered one of the 9 celestial bodies, the Navagraha, that influenced human destiny in Hindu astrology. The planet's red colour connected it to blood, energy, and vitality. Indian astronomers made sophisticated observations of Mars and calculated its orbital period with impressive accuracy. They noted that Mars took approximately 2 years to complete its journey through the zodiac, and they developed mathematical models to predict its position. The influence of Mangala was considered significant in determining a person's temperament, career, and marriage prospects, and this astrological tradition continues in India to this day. Across the ocean, the Maya civilization of Central America also watched Mars with great interest. Mayan astronomers tracked the planet's movements with extraordinary precision, recording their observations in codices and carved inscriptions. They calculated the synodic period of Mars, the time between successive oppositions as seen from Earth, to be 780 days, remarkably close to the modern value of 779.94 days. The Maya associated Mars with death and sacrifice, and its appearances and disappearances were incorporated into their complex calendar systems. Some scholars believe that certain Mayan rituals and even warfare were timed according to the position of Mars in the sky. What fascinated all these ancient cultures was the peculiar way Mars moved against the background stars. Unlike the Sun and Moon, which travel steadily in one direction through the constellations, Mars would periodically slow down, stop, reverse course for several weeks, stop again, and then resume its normal eastward motion. This retrograde motion puzzled ancient astronomers and led to elaborate theories about the structure of the cosmos. The Greeks developed complex systems of circles upon circles, epicycles, and deferents to explain how Mars could appear to move backward while actually travelling in perfect circular orbits. It would take nearly 2,000 years before the true explanation emerged, when Johannes Kepler realised that both Earth and Mars orbit the Sun in ellipses, and the retrograde motion is simply an illusion caused by Earth overtaking Mars in their respective orbits. The reddish colour of Mars also demanded explanation. Ancient peoples associated it with blood and fire, leading naturally to connections with war and violence. We now know that the colour comes from iron oxide, essentially rust, that covers much of the Martian surface. But for thousands of years that blood-red hue stirred the imaginations of humans gazing upward, reinforcing the planet's association with conflict and danger. As centuries passed and civilizations rose and fell, Mars remained a constant presence in the night sky. Medieval European astronomers inherited the Greek and Roman traditions, viewing Mars through the lens of Aristotelian cosmology, and Christian theology. The planet was thought to reside on a crystalline sphere that carried it around the Earth, which was believed to sit motionless at the centre of the universe. Astrologers continued to interpret the movements of Mars as omens, and its influence was considered malefic, associated with war, plague, and misfortune. The red planet's appearances were recorded in monastery chronicles and court documents, often in connection with disasters or political upheavals. During the Islamic Golden Age, Arab astronomers made significant advances in understanding planetary motion. They refined the mathematical models inherited from the Greeks, improving predictions of where Mars would appear in the sky. Astronomers like al-Battani and al-Biruni made careful observations and calculations that would later prove valuable to European scientists. They translated and preserved ancient Greek texts that might otherwise have been lost, ensuring that knowledge of Mars and other celestial bodies passed down through the generations. The Renaissance brought renewed interest in astronomy and a willingness to question ancient authorities. Nicolaus Copernicus proposed that the Sun, not the Earth, lay at the centre of the solar system, and that the planets, including Mars, orbited around it. This heliocentric model elegantly explained the retrograde motion of Mars without requiring complicated epicycles. When Earth, moving faster on its inner orbit, overtakes Mars, the red planet appears to move backward against the stars, just as a slower car seems to drift backward when you pass it on the highway. Copernicus published his revolutionary ideas in 1543, and while they were initially controversial, they set the stage for a complete transformation in our understanding of Mars and its place in the cosmos. Tycho Brahe, the great Danish astronomer of the late 16th century, made the most precise observations of Mars that had ever been achieved. Working before the invention of the telescope, Tycho used large, carefully calibrated instruments to track the planet's position with unprecedented accuracy. He accumulated years of data that would prove crucial for the next great leap in understanding. When Tycho died in 1601, his observations passed to his assistant, a brilliant mathematician named Johannes Kepler. Kepler spent years wrestling with Tycho's Mars data, trying to find a mathematical model that would accurately predict the planet's position. He was committed to finding the true nature of Mars's orbit, and he refused to accept any model that deviated from Tycho's observations by more than a tiny amount. After countless failed attempts using circular orbits, Kepler made a revolutionary discovery. Mars does not travel in a perfect circle around the Sun. Instead, it follows an ellipse with the Sun at one focus. This insight, published in 1609, became known as Kepler's first law of planetary motion. He also discovered that Mars moves faster when it is closer to the Sun and slower when it is farther away, sweeping out equal areas in equal times. These laws, derived primarily from studying Mars, applied to all the planets and fundamentally transformed astronomy from a descriptive enterprise into a predictive science. The same year Kepler published his laws, an Italian mathematician and natural philosopher named Galileo Galilei turned a new invention toward the heavens. The telescope, recently developed in the Netherlands, allowed Galileo to see celestial objects as no human ever had before. He observed the craters of the Moon, the phases of Venus, the moons of Jupiter, and the countless stars of the Milky Way. He also turned his telescope toward Mars, but the small instrument could reveal little detail on the distant red planet. Galileo noted that Mars appeared as a tiny disk rather than a point of light, confirming that it was a world with actual physical extent, but the surface features remained frustratingly beyond his reach. As telescope technology improved over the following decades, astronomers began to glimpse tantalizing hints of the Martian surface. In 1659, the Dutch scientist Christian Huygens made a drawing of Mars that showed a dark, triangular feature. This marking, which we now know as Syrtis Major, was the first surface feature of another planet ever recorded by a human being. Huygens observed that this feature returned to the same position after a period of time, allowing him to estimate that Mars rotated on its axis in approximately 24 hours, remarkably close to the length of an Earth day. This discovery suggested that Mars might be more Earth-like than anyone had previously imagined. Giovanni Cassini, the Italian-French astronomer who would later discover several moons of Saturn and the famous gap in Saturn's rings, also turned his attention to Mars. In 1666, he made careful observations that refined the estimate of Mars's rotation period to 24 hours and 40 minutes, within 3 minutes of the modern value. Cassini also observed the polar regions of Mars and noted that they appeared brighter than the rest of the planet, suggesting the presence of ice caps similar to those on Earth. These observations hinted at a world with seasons, weather, and perhaps even conditions suitable for life. The 18th century brought further advances in our understanding of Mars. William Herschel, the German-born British astronomer who discovered Uranus, made extensive observations of the red planet. He confirmed the existence of polar ice caps and noted that they changed in size over time, growing larger in winter and shrinking in summer. This seasonal variation strongly suggested that Mars experienced seasons similar to Earth's, a consequence of its axial tilt of about 25 degrees, very close to Earth's 23.5 degrees. Herschel also attempted to measure the Martian atmosphere, concluding that it was probably thinner than Earth's, but still substantial enough to support clouds and weather. Herschel's observations fueled speculation about the possibility of life on Mars. If the planet had seasons, polar ice caps, and an atmosphere, might it not also harbour living beings? Some astronomers and philosophers of the time embraced the idea of a plurality of worlds, suggesting that God would not have created so many planets only to leave them barren and lifeless. Mars, with its Earth-like characteristics, seemed a prime candidate for extraterrestrial inhabitants. These ideas remained purely speculative, but they planted seeds that would grow into a full-fledged obsession in the following century. As the 19th century progressed, telescope technology continued to improve, and astronomers dedicated increasing attention to Mars. In 1840, the German astronomers Wilhelm Beer and Johann Heinrich Mädler produced the first systematic map of the Martian surface. They carefully recorded the dark and light regions visible through their telescope, assigning names and creating a coordinate system that allowed features to be precisely located. Their map showed a world of contrasting terrains, with dark areas they interpreted as seas, and lighter regions they thought might be continents. While these interpretations would later prove incorrect, Beer and Mädler's work established Mars as a world with a complex and varied surface worthy of detailed study. The opposition of 1877 proved to be a watershed moment in the history of Mars observation. An opposition occurs when Mars and the Sun are on opposite sides of Earth, placing Mars at its closest approach and making it appear larger and brighter than at other times. The 1877 opposition was particularly favourable, bringing Mars closer to Earth than it had been in many years. Astronomers around the world prepared their telescopes for an intensive campaign of observation. At the United States Naval Observatory in Washington, D.C., Asaph Hall embarked on a systematic search for Martian moons. Previous astronomers had looked for satellites around Mars without success, and many had concluded that the planet had none. But Hall was persistent, using the observatory's large refracting telescope to scan the space around Mars night after night. His wife, Angelina, encouraged him to continue when he was ready to give up. On August 12, 1877, Hall spotted a tiny point of light near Mars that moved along with the planet. 6 nights later, he found a second moon. He named them Phobos and Deimos, Greek for fear and dread, after the mythological sons of Ares, who accompanied their father into battle. The discovery of these two small, irregularly shaped moons added new dimensions to our understanding of the Martian system. Meanwhile, in Milan, Italy, another astronomer was making observations that would shape perceptions of Mars for decades to come. Giovanni Schiaparelli, director of the Brera Observatory, turned his telescope toward Mars and began mapping its surface with unprecedented detail. He observed a network of linear features crossing the Martian surface, connecting the darker regions like lines on a map. Schiaparelli called these features canali, an Italian word that simply means channels and carries no implication of artificial origin. But when his observations were translated into English, canali became canals, a word that strongly suggests engineering and construction. This linguistic accident would have enormous consequences. Schiaparelli himself was cautious about interpreting the nature of the canali. He acknowledged that they might be natural features, perhaps geological formations or optical illusions. But others were less restrained. The idea that Mars might be crisscrossed by a network of artificial waterways built by an intelligent civilization to transport water from the polar ice caps to the arid equatorial regions captured the public imagination. Here was evidence, some believed, that we were not alone in the universe, that another world harboured beings capable of engineering on a planetary scale. No one embraced the canal theory more enthusiastically than Percival Lowell, a wealthy American businessman and amateur astronomer. Lowell came from a prominent Boston family and had the resources to pursue his interests on a grand scale. Fascinated by Schiaparelli's observations, Lowell decided to dedicate himself to the study of Mars. In 1894, he established an observatory in Flagstaff, Arizona, choosing the location for its clear, steady air at high altitude. Lowell Observatory became the center of Mars research in America, and Lowell himself became the planet's most vocal advocate. Lowell observed Mars obsessively, mapping hundreds of canals and developing an elaborate theory about Martian civilization. He believed that Mars was a dying world, its water supplies dwindling as the planet slowly dried out. The intelligent inhabitants facing extinction had constructed a vast network of canals to carry meltwater from the polar caps to irrigate their crops and sustain their cities. Lowell published his ideas in a series of popular books, including Mars in 1895, Mars and its Canals in 1906, and Mars as the Abode of Life in 1908. His vivid writing and romantic vision of a noble civilization struggling against cosmic fate captivated readers around the world. Not all astronomers accepted Lowell's interpretations. Many who observed Mars through their own telescopes could not see the canals that Lowell described in such detail. Edward Emerson, Barnard, one of the most skilled visual observers of his era, studied Mars extensively and saw no evidence of linear features. He suggested that the canals might be optical illusions, the tendency of the human eye to connect scattered dark spots into lines when viewing at the limits of resolution. Other astronomers pointed out that the canals seemed to become more numerous and elaborate with each passing opposition, suggesting that observers were seeing what they expected to see rather than what was actually there. The controversy over Martian canals raged for decades. Some astronomers supported Lowell's observations, while others dismissed them entirely. The debate became increasingly heated, with professional reputations and scientific credibility at stake. Meanwhile, the idea of intelligent Martians had escaped the astronomical community and taken root in popular culture. Newspapers reported breathlessly on each new canal discovery, and the public eagerly consumed stories about our neighbouring civilization. The canal controversy inspired some of the most influential science fiction ever written. In 1898 HG, Wells published The War of the Worlds, a novel depicting a Martian invasion of Earth. Wells imagined the Martians as highly advanced beings who had exhausted their own planet's resources and looked to Earth with envious eyes. His Martians were not the noble canal builders of Lowell's imagination, but terrifying creatures operating devastating war machines. The novel was a sensation, and its influence persists to this day. Orson Welles' famous 1938 radio adaptation caused panic among listeners who believed the fictional invasion was real, demonstrating the powerful hold that Mars had on the human imagination. Other writers took different approaches to the Red Planet. Edgar Rice Burroughs, creator of Tarzan, wrote a series of adventure novels set on Mars, which he called Barsoom. His Mars was a romantic world of ancient civilizations, beautiful princesses, and swashbuckling heroes. Ray Bradbury's The Martian Chronicles, published in 1950, offered a more melancholic vision of Mars as a place of fading beauty and lost opportunities. These literary works, and countless others, ensured that Mars remained central to humanity's dreams of space exploration and contact with alien life. As the 20th century progressed, improved telescopes and photographic techniques gradually undermined the canal theory. Photographs of Mars showed no evidence of the linear features that Lowell had mapped so carefully. The dark areas he had interpreted as vegetation sustained by canal water showed no seasonal changes consistent with growing crops. By the mid-20th century, most astronomers had concluded that the canals were indeed optical illusions, artifacts of the human visual system, struggling to interpret faint details at the limits of perception. Lowell's elaborate theory of a dying Martian civilization faded into history, though it left an indelible mark on popular culture. Yet even as the canals disappeared, Mars retained its allure. Astronomers continued to study the planet, measuring its atmosphere, tracking its dust storms, and mapping its surface features with increasing precision. Spectroscopic observations revealed that the Martian atmosphere was thin and composed largely of carbon dioxide, with little oxygen or water vapour. The surface pressure was found to be less than 1% of Earth's, too low for liquid water to exist. The romantic vision of a habitable Mars gave way to a harsher reality, a cold, dry, and apparently lifeless world. But even this diminished Mars held profound scientific interest. Understanding how Mars had evolved, why it had lost its water and thick atmosphere, could shed light on the history of Earth and the conditions necessary for life. And despite the inhospitable surface conditions, some scientists held out hope that life might exist in protected niches, perhaps underground or within the polar ice caps. The search for life on Mars, whether past or present, remained a driving motivation for planetary exploration. The story of Mars took a dramatic turn on July 14, 1965, when the American spacecraft Mariner 4 flew past the red planet and sent back the first close-up images of another world. The pictures were grainy and showed only a small portion of the surface, but they were revolutionary. Instead of the canals and vegetation that earlier observers had imagined, Mariner 4 revealed a cratered, moon-like landscape. Mars appeared ancient and dead, its surface pockmarked by billions of years of impacts. The thin atmosphere measured by Mariner 4's instruments confirmed that Mars was far more hostile to life than even the pessimists had predicted. The Mariner 4 results were sobering, but they represented only a tiny sample of the Martian surface. Subsequent missions would reveal a far more complex and interesting world. Mariner 6 and Mariner 7, which flew past Mars in 1969, returned more detailed images showing a variety of terrains. And in 1971, Mariner 9 became the first spacecraft to orbit another planet, arriving at Mars in the midst of a global dust storm. When the dust cleared, Mariner 9 revealed wonders that no one had anticipated. The spacecraft discovered enormous volcanoes, including Olympus Mons, the largest known volcano in the solar system. Rising 72,000 feet above the surrounding plains, Olympus Mons dwarfs anything on Earth. Its base would cover most of France, and its summit caldera could swallow a major city. The volcano's gentle slopes, built up over billions of years by countless lava flows, testify to the immense volcanic activity that once shaped Mars. 3 more giant volcanoes stand nearby on the Tharsis Bulge, a vast uplifted region that dominates one hemisphere of the planet. Mariner 9 also discovered Valles Marineris, a canyon system that stretches more than 2,500 miles across the Martian surface. If placed on Earth, Valles Marineris would span the entire United States from coast to coast. The canyon reaches depths of 4 miles in places, dwarfing the Grand Canyon, which would be lost as a minor tributary. The origin of Valles Marineris remains debated, but it likely formed through a combination of tectonic fracturing and erosion, possibly including catastrophic flooding. Most intriguingly, Mariner 9 revealed features that looked remarkably like dried riverbeds. Sinuous channels wound across the surface, complete with tributaries, and what appeared to be islands shaped by flowing water. Larger outflow channels suggested catastrophic floods of enormous scale, releasing more water in hours than the Mississippi River carries in years. These features provided the first strong evidence that liquid water had once flowed on the surface of Mars, raising profound questions about the planet's past climate and the possibility of ancient life. The discoveries of Mariner 9 transformed our understanding of Mars and set the stage for the next great leap in exploration. In 1976, 2 American spacecraft, Viking 1 and Viking 2, arrived at Mars carrying both orbiters and landers. For the first time, humanity would set instruments directly on the Martian surface and conduct experiments designed to search for life. The Viking landers touched down on opposite sides of the planet, Viking 1 in the Chryse Planitia region and Viking 2 in Utopia Planitia. They carried cameras that returned the first photographs from the surface of Mars, revealing a rocky, rust-coloured landscape beneath a pink sky. The images showed a world that was alien yet strangely familiar, a desert environment that might have been found in Arizona or the Sahara, except for the butterscotch-coloured sky and the utter absence of any visible life. The Viking landers carried 3 biology experiments designed to detect living organisms in the Martian soil. The gas exchange experiment moistened soil samples and monitored for gases that might be released by metabolizing organisms. The labeled release experiment added nutrients containing radioactive carbon to soil samples and looked for radioactive gases that would indicate biological activity. The pyrolytic release experiment exposed soil to carbon dioxide and carbon monoxide containing radioactive carbon, then heated the sample to see if any organic compounds had been synthesized, as would happen if photosynthetic organisms were present. The results of the Viking biology experiments were tantalizing and controversial. The labeled release experiment initially showed positive results, with radioactive gases being released from the soil samples. This seemed to suggest that something in the Martian soil was metabolizing the nutrients and releasing carbon dioxide, exactly what living organisms would do. But subsequent tests cast doubt on this interpretation. When the soil was heated to sterilize it, the reaction continued, suggesting a chemical rather than biological process. The other experiments showed no clear evidence of life, and a separate instrument designed to detect organic molecules found none in the Martian soil. Most scientists concluded that the Viking results were best explained by chemical reactions involving highly oxidizing compounds in the Martian soil, perhaps perchlorates or hydrogen peroxide produced by ultraviolet radiation. The harsh conditions on the surface, with intense ultraviolet light, extreme cold, and the absence of liquid water, seemed incompatible with life as we know it. The search for Martian life had apparently come up empty, yet the Viking results remained ambiguous enough to sustain hope. Gilbert Levin, the principal investigator for the labelled release experiment, maintained for decades that his experiment had detected life, and that the negative results from other instruments could be explained by the unusual chemistry of Martian organisms. While most of his colleagues disagreed, Levin's persistence kept the question open. The Viking missions had not proven that Mars was lifeless, only that life was not obviously present in the specific locations sampled. After Viking, Mars exploration entered a period of relative quiet. Budget constraints and shifting priorities meant that no new missions reached the planet for 2 decades. But scientists continued to study the data returned by Viking and earlier missions, developing new theories about Martian geology, climate, and the possibility of past life. The discovery of extremophils on Earth, organisms living in conditions previously thought impossible, expanded the range of environments where life might exist. Hot springs, deep ocean vents, Antarctic ice, and even rock miles below the surface were found to harbour life, suggesting that Mars might not be as hostile as it first appeared. In 1996, a startling announcement reignited interest in Martian life. A team of NASA scientists, led by David McKay, claimed to have found evidence of ancient microbial life in a meteorite from Mars. The meteorite, designated ALH 4001, had been collected in Antarctica in 1984 and was later identified as originating from Mars based on its chemical composition. The scientists reported finding tiny structures that resembled fossil bacteria along with mineral formations and organic compounds that they argued were best explained by biological activity. The announcement made headlines around the world and prompted President Bill Clinton to make a statement from the White House lawn. But the scientific community remained skeptical. Other researchers pointed out that the structures were far smaller than in any known bacteria, and that all the purported biosignatures could be explained by non-biological processes. The debate over ALH 84001 continued for years, with no clear resolution. Most scientists eventually concluded that the evidence for Martian life in the meteorite was not compelling, but the controversy demonstrated the intense interest in the question and the difficulty of proving or disproving the existence of extraterrestrial life. The late 1990s brought a new wave of Mars exploration. In 1997, Mars Pathfinder landed on the red planet carrying Sojourner, the first rover ever to explore another world. This small microwave oven-sized vehicle captured the imagination of millions as it rolled across the Martian surface, examining rocks and soil in the Ares Valles region. The mission demonstrated that relatively inexpensive spacecraft could successfully reach Mars and conduct meaningful science, opening a new era of exploration that continues to this day. Chapter 7: The Robotic Exploration Era. Orbiters that changed everything. As we settle deeper into the story of Mars, let us turn our attention to the spacecraft that have circled this distant world, peering down from above with ever more sophisticated instruments. These orbiters have mapped every inch of the Martian surface, measured the composition of its atmosphere, tracked its weather patterns, and discovered secrets that would have seemed like science fiction to earlier generations. The view from orbit has transformed Mars from a mysterious red dot in the night sky into a world we know with remarkable intimacy. The journey of orbital exploration began with Mariner 9, which we touched upon earlier, but the true golden age of Mars orbiters commenced in the 1990s and continues to the present day. Each mission has built upon the discoveries of its predecessors, creating an ever more detailed portrait of our neighbouring world. Mars Global Surveyor arrived at the Red Planet in September 1997, beginning a mission that would last nearly a decade and revolutionise our understanding of Martian geology and climate. This spacecraft carried a suite of instruments designed to study Mars with unprecedented precision. Its laser altimeter measured the topography of the entire planet, creating three-dimensional maps that revealed the true scale of Martian landforms. The data showed that the northern hemisphere of Mars sits several miles lower than the southern hemisphere, a dramatic difference known as the Martian dichotomy that remains one of the planet's greatest mysteries. The camera aboard Mars Global Surveyor captured images with resolution fine enough to see objects the size of a small car. Scientists poring over these images discovered features that suggested liquid water had flowed on Mars far more recently than anyone had expected. Gullies carved into crater walls, and cliff faces appeared fresh and uneroded, leading some researchers to propose that groundwater might occasionally seep to the surface, even under present conditions. These findings sparked intense debate about the possibility of liquid water on modern Mars and reinvigorated the search for environments where life might survive. Mars Global Surveyor also discovered that Mars lacks a global magnetic field like Earth's, but retains patches of magnetism in its ancient southern crust. These magnetic anomalies are remnants of a time when Mars did possess a global magnetic field, generated by a churning molten core. The field appears to have shut down approximately 4 billion years ago, leaving the planet vulnerable to the solar wind that has slowly stripped away its atmosphere. Understanding when and why Mars lost its magnetic field is crucial to understanding why the planet evolved so differently from Earth. The spacecraft operated far beyond its planned mission lifetime, continuing to return valuable data until November 2006, when contact was lost after nearly 10 years of service. Mars Global Surveyor had fundamentally changed our view of Mars, revealing a world of surprising complexity and ongoing geological activity. While Mars Global Surveyor was still operating, another orbiter arrived to join the investigation. Mars Odyssey, launched in 2001, reached the Red Planet in October of that year and remains operational to this day, making it the longest-serving spacecraft at Mars. The mission's primary scientific goal was to map the distribution of chemical elements and minerals on the Martian surface, with particular attention to hydrogen, which could indicate the presence of water ice. The gamma-ray spectrometer aboard Mars Odyssey made a discovery of profound importance. It detected vast quantities of hydrogen just below the surface in the polar regions, strongly suggesting the presence of water ice mixed with the soil. Subsequent observations confirmed that ice exists not just at the poles, but extends to surprisingly low latitudes, hidden beneath a thin layer of dry soil. This subsurface ice represents a significant water reservoir that could prove invaluable for future human explorers and might provide habitats for any Martian life that exists today. Mars Odyssey also carries a thermal imaging system that has mapped the entire planet in infrared wavelengths. These observations reveal the mineral composition of the surface and help scientists understand the geological processes that have shaped Mars over billions of years. The spacecraft continues to serve as a crucial communications relay for landers and rovers on the surface, demonstrating the value of maintaining long-term orbital assets at Mars. The European Space Agency entered Mars exploration with Mars Express, which arrived at the Red Planet in December 2003. This mission represented Europe's first successful venture to another planet and has proven remarkably productive. Mars Express carries a high-resolution stereo camera that has captured stunning three-dimensional images of the Martian surface, revealing the intricate details of canyons, volcanoes, and impact craters with breathtaking clarity. One of the most significant instruments aboard Mars Express is the Marsis radar, designed to probe beneath the Martian surface. In 2018, scientists announced that Marsis had detected what appeared to be a lake of liquid water buried beneath the South Polar ice cap, approximately 1 mile below the surface. The discovery was extraordinary, suggesting that liquid water might exist on Mars today, kept from freezing by the pressure of overlying ice and possibly by dissolved salts that lower its freezing point. Subsequent observations have identified additional subsurface reflections that might indicate more buried lakes, though some scientists have proposed alternative explanations involving unusual geological materials. The debate continues, but the possibility of subsurface liquid water has profound implications for the search for Martian life. Mars Express also made important discoveries about the Martian atmosphere. Its instruments detected methane, a gas that on Earth is primarily produced by living organisms, though it can also be generated by geological processes. The presence of methane on Mars is puzzling because the gas should be destroyed by ultraviolet radiation within a few hundred years. Its continued presence suggests an ongoing source, either biological or geological, that replenishes the supply. Identifying this source remains one of the most tantalizing mysteries in Mars science. The Mars Reconnaissance Orbiter, which arrived in 2006, brought the most powerful camera ever sent to another planet. The high-resolution imaging science experiment, known as HiRISE, can photograph objects on the Martian surface as small as a dinner table. The images returned by HiRISE have revealed Mars in stunning detail, showing individual boulders, rippling sand dunes, and the tracks left by rovers crawling across the surface. Scientists have used HiRISE to study active processes on Mars, including avalanches, dust devils, and the seasonal appearance and disappearance of dark streaks on crater walls. These dark streaks, known as recurring slope lineae, generated tremendous excitement when they were first discovered. They appear during warm seasons and fade during cold seasons, following a pattern consistent with flowing liquid water. For years, scientists debated whether the streaks might be caused by briny water seeping from underground aquifers. However, more recent analysis suggests that the features are more likely caused by dry granular flows, essentially small landslides of sand and dust. The mystery is not entirely resolved, but the current consensus leans toward dry processes rather than liquid water. Mars Reconnaissance Orbiter has also proven invaluable for selecting landing sites for surface missions. Its detailed images allow scientists to identify safe, scientifically interesting locations where landers and rovers can touch down without encountering hazardous terrain. The spacecraft serves as the primary communications relay for surface missions, transmitting data from rovers back to Earth at high speeds. The MAVEN mission, which stands for Mars Atmosphere and Volatile Evolution, arrived at Mars in 2014 with a specific focus on understanding how the planet lost its atmosphere. Unlike earlier orbiters that studied the surface, MAVEN dips into the upper atmosphere, directly sampling the gases that are escaping into space. The mission has confirmed that the solar wind is stripping away the Martian atmosphere at a significant rate, and that this process has been occurring for billions of years. MAVEN's measurements allow scientists to extrapolate backward in time, estimating how much atmosphere Mars has lost over its history. The results suggest that early Mars possessed a much thicker atmosphere, perhaps thick enough to support liquid water on the surface and create the river valleys and lake beds we see preserved in the ancient terrain. The loss of this atmosphere, driven by the absence of a protective magnetic field, transformed Mars from a potentially habitable world into the cold, dry desert we see today. Understanding this process helps scientists assess the habitability of planets around other stars and the long-term prospects for life beyond Earth. India's Mars Orbiter mission, affectionately known as Mangalyaan, arrived at Mars in September 2014, making India the fourth space agency to successfully reach the Red Planet and the first to do so on its maiden attempt. The mission was remarkable for its low cost, demonstrating that meaningful planetary exploration can be achieved without enormous budgets. Mangalyaan carried instruments to study the Martian surface and atmosphere, contributing to the international effort to understand our neighbouring world. The United Arab Emirates joined the Mars exploration community in 2021 with the HOPE orbiter, also known as the Emirates Mars mission. HOPE was designed to study the Martian atmosphere and weather, providing a global view of how conditions change throughout the day and across the seasons. The mission represents the UAE's ambitions in space exploration and has returned valuable data about dust storms, atmospheric dynamics, and the behaviour of hydrogen and oxygen in the upper atmosphere. China's Tianwen-1 mission, which also arrived in 2021, included both an orbiter and a lander with a rover. The orbiter carries instruments to study the Martian surface, subsurface, and atmosphere, contributing to the growing body of knowledge about Mars. The successful deployment of the Zhurong rover marked China's first surface mission to another planet, demonstrating the nation's rapidly advancing space capabilities. Together, these orbiters have created an unprecedented picture of Mars. We now have detailed maps of the entire surface, showing every crater, volcano, canyon, and sand dune. We understand the composition of the rocks and soil, the structure of the atmosphere, and the behaviour of the climate. We have identified regions where water ice lies just below the surface, and locations where liquid water may once have pooled in lakes and seas. This knowledge, accumulated over decades of patient observation, sets the stage for the next chapter in Mars exploration, the missions that have touched the surface itself. Chapter 8. Landers and Rovers, Touching the Martian Surface. There is something profoundly moving about setting a spacecraft down on another world. Orbiters can study a planet from above, measuring and mapping with remarkable precision. But landing brings us into direct contact with alien soil, allowing us to examine rocks up close, dig into the ground, and experience the environment in ways that orbital observation cannot match. The landers and rovers that have reached Mars represent some of humanity's greatest technological achievements, and their discoveries have transformed our understanding of the Red Planet. The Viking landers of 1976 were the first spacecraft to successfully operate on the Martian surface for an extended period. We discussed their biology experiments earlier, but these remarkable machines accomplished far more than searching for life. They monitored Martian weather for years, recording temperatures, pressures, and wind speeds that revealed the daily and seasonal rhythms of the planet. They photographed their surroundings in detail, showing a rocky landscape strewn with boulders and blanketed by fine rust-coloured dust. They analysed the composition of the soil, finding it rich in iron, silicon, and other elements, but lacking the organic compounds that are abundant in Earth's soil. Viking 1 operated on the surface for over 6 years, finally falling silent in November 1982 when a faulty command accidentally shut down its communications system. Viking 2 lasted until April 1980 when its batteries failed after the solar panels became covered with dust. These missions demonstrated that spacecraft could survive the harsh Martian environment for extended periods and laid the groundwork for all the surface missions that followed. After Viking, 2 decades passed before another spacecraft successfully landed on Mars. The Mars Polar Lander and the British Beagle 2 were lost during landing attempts, reminding everyone of the difficulty of reaching the Martian surface. But in 1997, Mars Pathfinder achieved a successful landing using an innovative airbag system that allowed the spacecraft to bounce to a stop on the rocky terrain of Ares Vallis. Mars Pathfinder carried Sojourner, a small rover about the size of a microwave oven and weighing just 23 pounds. This tiny vehicle was the first wheeled robot to explore another planet, and it captured the imagination of people around the world. Millions followed the mission online, watching as Sojourner rolled up to rocks with names like Barnacle Bill and Yogi, examining them with its instruments. The rover operated for nearly 3 months, far exceeding its planned 1-week mission, and travelled a total distance of about 330 feet from the lander. Sojourner's scientific instruments analysed the composition of Martian rocks and soil, finding evidence of a complex geological history. Some rocks appeared to be volcanic in origin, while others showed signs of being shaped by water. The mission demonstrated that rovers could successfully navigate the Martian terrain and conduct meaningful science, paving the way for much more ambitious vehicles to follow. The twin rovers Spirit and Opportunity landed on Mars in January 2004, beginning missions that would far exceed anyone's expectations. These golf cart-sized vehicles were designed to operate for 90 Martian days, just long enough to drive a few hundred feet and examine a handful of rocks. Instead, they explored for years, covering miles of terrain and making discoveries that fundamentally changed our understanding of Mars. Spirit landed in Gusev Crater, a basin that scientists believed might once have held a lake fed by a massive channel called Mardim Vallis. The rover found a landscape dominated by volcanic rocks, initially disappointing researchers who had hoped to find sediments deposited by water. But as Spirit drove toward a range of hills on the horizon, it began to find evidence of past water activity. Rocks showed signs of alteration by acidic water, and mineral deposits suggested that hot springs or steam vents had once existed in the area. Spirit continued exploring until 2010, when it became stuck in soft soil and could no longer position its solar panels to survive the Martian winter. Opportunity landed on the opposite side of Mars in a small crater on Meridiani Planum. Almost immediately, the rover made a stunning discovery. The walls of the crater exposed layers of sedimentary rock, the first ever found on Mars. These rocks contain tiny spheres of height, an iron-rich mineral that typically forms in the presence of water. The spheres, nicknamed blueberries by the science team, were scattered across the surface like marbles on a playground. Opportunity had landed in a place where water had once soaked the ground, leaving behind unmistakable evidence of its presence. Over the following years, Opportunity drove from crater to crater, examining rocks and sediments that told the story of ancient Mars. The rover found more evidence of past water, including minerals that form only in wet environments and rock textures that indicated flowing or standing water. Opportunity also discovered meteorites sitting on the Martian surface, chunks of iron that had fallen from space and lay undisturbed for millions of years. Opportunity's journey became legendary. The rover drove more than 28 miles across the Martian surface, setting a record for the longest distance travelled by any off-Earth wheeled vehicle. It explored craters large and small, climbed hills, and descended into valleys. The mission lasted not 90 days, but nearly 15 years, finally ending in June 2018, when a global dust storm blocked sunlight from the rover's solar panels. NASA made hundreds of attempts to contact Opportunity after the storm cleared, but the rover never responded. The mission was officially declared complete in February 2019, ending one of the most successful planetary exploration campaigns in history. The Phoenix lander touched down near the Martian North Pole in May 2008, targeting a region where orbital observations suggested ice lay just below the surface. Unlike the rovers, Phoenix was a stationary lander, unable to drive across the terrain. Instead, it carried a robotic arm designed to dig trenches in the soil and deliver samples to onboard instruments for analysis. Phoenix quickly confirmed what orbiters had suspected. Just a few inches below the surface, the lander's arm uncovered bright white material that slowly disappeared over several days. This could only be water ice, sublimating directly into the thin Martian atmosphere as it was exposed to sunlight. For the first time, a spacecraft had directly observed water ice on Mars, confirming that the polar regions hold vast reserves of frozen water. The lander's instruments also detected perchlorates in the Martian soil, highly reactive chlorine compounds that have important implications for both the search for life and future human exploration. Perchlorates could destroy organic molecules, potentially explaining why the Viking landers found no organic compounds even if life exists on Mars. On the other hand, certain microorganisms on Earth can use perchlorates as an energy source, suggesting that Martian life might have evolved to exploit this unusual chemistry. For human explorers, perchlorates pose a health risk, but could also be useful as rocket propellant or for generating oxygen. Phoenix operated for about 5 months before the approaching Martian. Winter brought darkness and cold that the solar-powered lander could not survive. The mission had accomplished its goals, confirming the presence of water ice and providing new insights into the chemistry of the Martian soil. The Curiosity rover, which landed in August 2012, represented a dramatic leap in capability compared to earlier surface missions. About the size of a small car and weighing nearly a ton, Curiosity was too large to land using airbags like Pathfinder and the twin rovers. Instead, NASA developed an audacious landing system called the Sky Crane. After entering the Martian atmosphere and slowing with a parachute, the spacecraft's descent stage fired rockets to hover above the surface while lowering Curiosity on cables. Once the rover's wheels touched down, the cables were cut and the descent stage flew away to crash at a safe distance. The entire sequence, which had never been attempted before, worked flawlessly. Curiosity landed in Gale Crater, a 96-mile-wide basin with a 3-mile-high mountain of layered sediments at its centre. This mountain, named Olympus Mons, but informally called Mount Sharp, preserves a record of Martian geological history spanning billions of years. By driving up the mountain and examining the layers in sequence, Curiosity can read this record like pages in a book. Understanding how conditions on Mars changed over time, the rover carries the most sophisticated suite of scientific instruments ever sent to another planet. It can drill into rocks and analyze their composition, identifying minerals and detecting organic molecules. It can measure radiation levels, monitor weather conditions, and photograph its surroundings in stunning detail. Unlike earlier rovers that relied on solar power, Curiosity carries a radioisotope thermoelectric generator that converts heat from decaying plutonium into electricity, allowing the rover to operate day and night, through dust storms and winter darkness. Curiosity's discoveries have been remarkable. Within months of landing, the rover found evidence that Gale Crater once contained a lake of fresh water that could have supported microbial life. The rocks at the landing site showed clear signs of having formed in a watery environment, with fine-grained sediments and minerals that require water to form. As Curiosity drove toward Mount Sharp, it found more evidence of past water, including ancient stream beds where rounded pebbles had been tumbled by flowing water. The rover has also detected organic molecules in Martian rocks, the complex carbon-based compounds that are the building blocks of life as we know it. While these molecules do not prove that life ever existed on Mars, they demonstrate that the raw materials for life were present. Curiosity has also detected seasonal variations in methane levels in the Martian atmosphere, adding to the mystery of where this gas comes from and whether it might have a biological source. As of late 2025, Curiosity continues to operate, climbing higher on Mount Sharp and examining ever more ancient layers of rock. The rover has travelled more than 20 miles and shows no signs of stopping, though its wheels have accumulated significant damage from the sharp Martian rocks. The mission has already lasted more than 13 years, far exceeding its planned 2-year primary mission, and continues to return valuable science data. The InSight lander arrived on Mars in November 2018 with a mission unlike any that had come before. Rather than studying the surface, InSight was designed to investigate the deep interior of Mars using seismology to probe the planet's structure. The lander carried a sensitive seismometer that could detect the faint vibrations of Marsquakes, along with a heat probe intended to measure how much heat flows from the planet's interior. InSight successfully deployed its seismometer and began listening for Marsquakes. Over the following years, the instrument detected hundreds of seismic events, revealing that Mars is a geologically active world with ongoing tectonic activity. The data allowed scientists to determine the size and composition of Mars's core, mantle, and crust, providing the first detailed picture of the internal structure of another rocky planet. The core proved to be larger and less dense than expected, suggesting it contains significant amounts of lighter elements mixed with iron. The heat probe, unfortunately, encountered unexpected difficulties. It was designed to hammer itself into the ground, but the Martian soil at the landing site proved too clumpy and failed to provide the friction needed for the probe to dig. Despite years of creative attempts to help the probe penetrate deeper, it never reached its target depth, and that part of the mission was eventually abandoned. Nevertheless, InSight's seismic observations alone made the mission a tremendous success. InSight operated until December 2022, when dust accumulation on its solar panels reduced power to the point where the lander could no longer function. The mission had achieved its primary goal of understanding the Martian interior, adding a crucial dimension to our knowledge of the Red Planet. The Perseverance rover landed in Jezero crater in February 2021, carrying the most advanced instruments ever sent to Mars and a companion that would make history. Jezero crater was chosen because orbital observations showed clear evidence that it once contained a lake fed by a river that carved a delta into the crater floor. Deltas are particularly promising places to search for signs of ancient life because they concentrate and preserve organic material carried by flowing water. Perseverance is similar in design to Curiosity, but carries a different suite of instruments optimized for astrobiology, the search for signs of past life. The rover can analyze rocks in unprecedented detail, identifying minerals and organic compounds at microscopic scales. Most importantly, Perseverance is collecting samples of Martian rock and soil, sealing them in tubes that will eventually be returned to Earth by a future mission. These samples will allow scientists to study Martian materials in laboratories with instruments far more sophisticated than anything that can be sent to Mars, potentially revealing definitive evidence of ancient life if it exists. The companion that accompanied Perseverance was Ingenuity, a small helicopter designed to demonstrate powered flight in the thin Martian atmosphere. With an atmospheric pressure less than 1% of Earth's, Mars presents extreme challenges for aircraft. Ingenuity's rotors had to spin at nearly 2,500 revolutions per minute to generate enough lift, compared to about 500 revolutions per minute for a typical Earth helicopter. On April 19, 2021, Ingenuity lifted off from the Martian surface, rose to a height of about 10 feet, hovered for 30 seconds, and landed safely. It was the first powered, controlled flight on another planet, a Wright brothers moment for the space age. What was planned as a 30-day technology demonstration turned into a multi-year operational mission, with Ingenuity flying more than 70 times and scouting terrain ahead of Perseverance. The helicopter finally ended its mission in January 2024 when one of its rotor blades was damaged during landing, but it had far exceeded all expectations and proven that aerial exploration of Mars is possible. Perseverance continues to explore Jezero Crater, examining the ancient delta deposits and collecting samples that may contain evidence of past life. The rover has found rocks that show clear signs of having formed in water, including sediments that preserve the shapes of ancient ripples and minerals that indicate a complex history of wet and dry periods. Whether these rocks contain fossils of ancient Martian microbes remains to be determined, but the samples Perseverance is collecting will eventually provide answers. China's Zhurong rover landed on Mars in May 2021 as part of the Tianwen-1 mission, making China the second country to successfully operate a rover on the Martian surface. Zhurong landed in Utopia Planitia, not far from where Viking 2 touched down in 1976. The rover carried instruments to study the composition and structure of the Martian soil, including a ground-penetrating radar that could image the subsurface. Zhurong operated for about 1 Earth year, travelling more than a mile across the Martian surface. The rover found evidence of water activity in the relatively recent geological past, suggesting that Utopia Planitia experienced flooding or groundwater seepage within the last few 100 million years. Zhurong entered hibernation mode in May 2022 as the Martian winter approached, and as of late 2025, China has not announced whether the rover has resumed operations. These landers and rovers have transformed Mars from an abstract destination into a place we know intimately. We have seen its rust-coloured rocks up close, watched dust devils dance across its plains, and traced the paths of ancient rivers, now dry for billions of years. Each mission has built upon the discoveries of its predecessors, creating an ever more detailed understanding of our neighbouring world. And the exploration continues, with new missions planned and humanity's first footsteps on Mars perhaps only decades away. Chapter 9. The Moons of Mars, Phobos and Deimos. As we drift further into the story of Mars, let us turn our attention to the 2 small moons that circle the red planet. Phobos and Deimos, named for the Greek gods of fear and dread, are among the smallest moons in the solar system. Yet they hold important clues about the history of Mars and the evolution of our cosmic neighbourhood. These tiny worlds, visible only as points of light from Earth, have been photographed in detail by spacecraft orbiting Mars, revealing surfaces scarred by impacts and shaped by forces we are only beginning to understand. The discovery of the Martian moons came during the favourable opposition of 1877, the same period that saw Giovanni Schiaparelli begin his controversial mapping of Martian canals. Asaph Hall, an astronomer at the United States Naval Observatory in Washington, D.C., had been searching for Martian satellites without success. Other astronomers had looked before and found nothing, leading many to conclude that Mars had no moons. Hall was about to give up when his wife, Angelina, encouraged him to continue. On the night of August 12, 1877, Hall spotted a faint point of light near Mars that moved along with the planet. 6 nights later, he found a second moon. The discovery made headlines around the world and added new dimensions to our understanding of the Martian system. Hall named the moons Phobos and Deimos after the sons of Ares in Greek mythology. According to legend, Phobos and Deimos accompanied their father into battle, spreading fear and terror among his enemies. The names proved fitting for these small dark bodies that had eluded detection for so long. Phobos, the larger and inner moon, orbits remarkably close to Mars. At a distance of only about 3,700 miles from the planet's surface, Phobos circles Mars faster than the planet rotates, completing one orbit in just 7 hours and 39 minutes. This means that from the Martian surface, Phobos rises in the west and sets in the east, the opposite of what we see with our own moon. An observer on Mars would watch Phobos cross the sky in about 4 hours, its motion clearly visible against the background stars. Phobos is a small world, measuring roughly 17 miles across at its widest point. Its shape is irregular, more like a lumpy potato than a sphere, because its gravity is too weak to pull it into a round form. The surface is extremely dark, reflecting only about 7% of the sunlight that falls on it, making Phobos one of the least reflective bodies in the solar system. This darkness suggests a composition rich in carbon compounds, similar to certain types of asteroids. The most striking feature on Phobos is Stickney, an impact crater nearly 6 miles across, almost half the diameter of the Moon itself. The impact that created Stickney must have come close to shattering Phobos entirely. Grooves radiate outward from the crater, stretching across much of the Moon's surface. Scientists have debated whether these grooves were caused by the Stickney impact, by tidal stresses from Mars's gravity, or by impacts from debris ejected from the Martian surface. Recent research suggests that the grooves may be chains of smaller craters created by material blasted off Mars by asteroid impacts, falling back onto Phobos over millions of years. Phobos orbits so close to Mars that it is slowly spiraling inward, drawn by tidal forces that sap energy from its orbit. In approximately 50 million years, Phobos will either crash into Mars or, more likely, be torn apart by tidal stresses as it crosses the Roche limit, the distance within which a moon cannot hold itself together against the gravitational pull of its planet. The debris from Phobos's destruction would form a ring around Mars, transforming the red planet into a ringed world for a time before the material eventually falls to the surface. Deimos, the smaller and outer moon, orbits at a distance of about 14,500 miles from Mars, completing one circuit in about 30 hours. This is only slightly longer than a Martian day, so from the surface, Deimos rises in the east and sets in the west like our own moon, but it moves so slowly that it takes nearly 3 days to cross the sky. Deimos is tiny, measuring only about 9 miles across, and like Phobos it has an irregular shape and a very dark surface. Deimos appears smoother than Phobos, with fewer visible craters and a thick layer of fine dust, called regolith, that blankets its surface. The two largest craters on Deimos, named Swift and Voltaire, after writers who predicted the existence of Martian moons before they were discovered, are only about 1 mile and 2 miles across respectively. The relative smoothness of Deimos may result from the thick regolith filling in and obscuring smaller craters over time. Unlike Phobos, Deimos is slowly moving away from Mars. Its orbit lies beyond the synchronous orbit distance, where a moon's orbital period matches the planet's rotation period, so tidal forces are gradually pushing it outward. Eventually, Deimos may escape Mars's gravity entirely and become an independent asteroid orbiting the Sun, though this process will take billions of years. The origin of Phobos and Deimos remains one of the enduring mysteries of planetary science. 3 main hypotheses have been proposed, each with strengths and weaknesses. The first hypothesis suggests that the moons are captured asteroids. Their dark surfaces and irregular shapes resemble certain types of asteroids found in the outer asteroid belt, and their compositions, as inferred from spectroscopic observations, are consistent with carbon-rich asteroids. However, capturing an asteroid into a stable circular orbit like those of Phobos and Deimos is dynamically difficult. An asteroid approaching Mars would typically either crash into the planet or swing past on a hyperbolic trajectory, escaping back into interplanetary space. Capture would require some mechanism to slow the asteroid down, such as atmospheric drag or a three-body interaction, and neither explanation seems entirely satisfactory. The second hypothesis proposes that Phobos and Deimos formed from debris blasted off Mars by a giant impact. Mars bears the scars of several enormous impacts, including the Borealis Basin, which may cover most of the northern hemisphere, and the Hellas Basin in the south. A sufficiently large impact could have ejected enough material into orbit to coalesce into moons. This scenario would explain the circular equatorial orbits of Phobos and Deimos, which are difficult to achieve through capture. However, material ejected from Mars should have a composition similar to the Martian crust, which does not match the dark carbon-rich surfaces of the moons. The third hypothesis suggests that the moons formed from a debris disk that surrounded Mars early in its history, similar to how Earth's moon is thought to have formed from debris created by a giant impact. This scenario could produce moons with the observed orbits, but it faces the same compositional challenges as the impact ejection hypothesis. Recent observations and computer simulations have not definitively resolved the question. Some researchers have proposed hybrid scenarios, such as the capture of an asteroid that was subsequently reshaped by tidal forces and impacts. Others suggest that the dark surface material on Phobos and Deimos may be a thin veneer of space-weathered material that obscures a different composition beneath. Definitive answers may require sample return missions that bring pieces of the moons back to Earth for detailed analysis. Several spacecraft have observed Phobos and Deimos during their missions to Mars. The Viking orbiters photographed both moons in the 1970s, revealing their irregular shapes and cratered surfaces. Mars Global Surveyor, Mars Express, and Mars Reconnaissance Orbiter have all captured detailed images, showing features as small as a few feet across. These observations have revealed the grooves on Phobos, the smooth regolith of Deimos, and the complex surface textures of both moons. The Soviet Union attempted to send dedicated missions to Phobos in the late 1980s. Phobos 1 was lost during its journey to Mars due to a software error. Phobos 2 successfully entered orbit around Mars and returned images of Phobos before contact was lost, just as the spacecraft was preparing to release landers onto the moon's surface. These failures highlighted the difficulty of exploring the Martian moons, but interest in Phobos and Deimos has remained strong. Japan's space agency, JAXA, is developing a mission called Martian Moons Exploration, or MMX, scheduled to launch in the mid-2020s. This ambitious mission will orbit Phobos, land on its surface, collect samples, and return them to Earth. The samples will allow scientists to determine the composition of Phobos with far greater precision than remote observations permit, potentially resolving the mystery of the moon's origin. If Phobos proves to be a captured asteroid, its samples will provide insights into the primordial materials from which the solar system formed. If it originated from Mars, the samples will offer a window into the early history of the red planet. The moons of Mars also hold practical interest for future human exploration. Phobos, in particular, could serve as a staging base for missions to the Martian surface. Its low gravity would make landing and launching relatively easy, and its proximity to Mars would allow astronauts to operate rovers and other equipment on the surface with minimal communication delay. Water ice, if present in Phobos's interior, could be extracted and used for drinking water, oxygen, and rocket fuel. Some mission planners have proposed establishing a permanent human presence on Phobos as a stepping stone to the eventual settlement of Mars itself. Deimos, though smaller and more distant, offers its own advantages. Its position beyond synchronous orbit means it experiences less gravitational stress from Mars, potentially making it a more stable location for long-term infrastructure. The thick regolith covering Deimos could provide radiation shielding for habitats, protecting astronauts from the cosmic rays and solar particle events that pose significant health risks during extended space missions. Some visionaries have even suggested hollowing out portions of Deimos to create pressurized living spaces, using the Moon's own material as building blocks for a permanent settlement. The exploration of Phobos and Deimos represents a natural extension of our robotic investigation of Mars. These small moons, once mere points of light glimpsed through 19th century telescopes, have become worlds in their own right, with their own mysteries to solve and their own potential to contribute to humanity's future in space. As we continue our journey through the story of Mars, we carry with us the knowledge that the red planet does not travel alone through the cosmos. Its two small companions, fear and dread, made manifest in rock and dust, accompany it on its endless orbit around the Sun. Chapter 10. The Formation and Ancient History of Mars. Let us now journey backward through time, far beyond human history, beyond the age of dinosaurs, beyond even the formation of life on Earth. We travel to the very beginning, when our solar system was nothing more than a vast cloud of gas and dust drifting through the galaxy. Understanding how Mars came to be requires us to understand how all the planets formed, emerging from chaos and violence to become the worlds we know today. Approximately 4.6 billion years ago, a region of the Milky Way galaxy contained a molecular cloud, an enormous accumulation of hydrogen, helium, and heavier elements produced by generations of stars that had lived and died before our Sun was born. Something disturbed this cloud, perhaps the shockwave from a nearby supernova or the gravitational influence of a passing star. Whatever the cause, the disturbance triggered a collapse. Gravity pulled the gas and dust inward, concentrating matter at the centre of the collapsing region. As the material fell inward, it began to spin, conserving angular momentum like a figure skater pulling in their arms. The spinning cloud flattened into a disk, with most of the mass concentrated at the centre. This central concentration grew hotter and denser as gravity compressed it further, until temperatures and pressures became high enough to ignite nuclear fusion. Hydrogen atoms began fusing into helium, releasing enormous amounts of energy. Our Sun was born. The disk of material surrounding the young Sun, called the protoplanetary disk or solar nebula, contained the raw ingredients from which the planets would form. Close to the Sun, where temperatures were high, only rocky materials and metals could exist in solid form. Volatile substances like water, ammonia, and methane remained gaseous and were swept outward by the solar wind. Farther from the Sun, beyond a boundary called the frost line, temperatures were cold enough for these volatiles to condense into ice. This temperature gradient would determine the fundamental nature of the planets, with small rocky worlds forming in the inner solar system and giant, gas-rich planets forming in the outer regions. Within the disk, solid particles began to stick together through gentle collisions, a process called accretion. Dust grains accumulated into pebbles, pebbles into boulders, and boulders into bodies miles across called planetesimals. These planetesimals were the building blocks of planets, and they continue to grow through collisions with one another. Some collisions were constructive, merging two bodies into one. Others were destructive, shattering planetesimals into fragments that would later be swept up by larger bodies. Over millions of years, a few planetesimals in each region of the disk grew large enough that their gravity began to dominate their surroundings. These planetary embryos, as scientists call them, attracted material from ever wider feeding zones, growing rapidly through a process called runaway accretion. In the inner solar system, several dozen planetary embryos emerged, each roughly the size of the Moon or Mars. These embryos continue to interact gravitationally, their orbits becoming increasingly chaotic until they began to collide with one another in giant impacts. Mars formed from one or more of these planetary embryos, accumulating most of its mass within the first few million years of solar system history. Unlike Earth and Venus, which grew to their present sizes through numerous giant impacts over tens of millions of years, Mars appears to have formed quickly and then stopped growing. Analysis of Martian meteorites suggests that Mars reached approximately half its present size within just 2 million years of the solar system's formation, and it was essentially complete within 10 million years. This rapid formation may explain why Mars is so much smaller than Earth and Venus. By the time the larger planets finished assembling, Mars had already cleared its orbital neighbourhood and had no more material to accrete. The early Mars was a violent world. The final stages of accretion involved impacts of tremendous energy, collisions that melted large portions of the planet and released enough heat to keep the entire world molten for an extended period. This global magma ocean allowed dense materials, primarily iron and nickel, to sink toward the centre, forming a metallic core. Lighter silicate materials floated to the surface, eventually cooling to form the rocky mantle and crust. This process of differentiation, the separation of a planet into layers of different density and composition, occurred on all the terrestrial planets and is responsible for their basic internal structure. As Mars cooled, a solid crust formed on the surface of the magma ocean. Volcanic activity was intense during this period, with molten rock erupting through the thin crust and spreading across the surface. Gases dissolved in the magma, including water vapour, carbon dioxide, nitrogen, and sulfur compounds, escaped into the atmosphere, creating a thick envelope of air around the young planet. This early atmosphere may have been dense enough to support liquid water on the surface, raising the possibility that Mars was habitable almost from the moment it formed. The early solar system remained a dangerous place even after the planets had largely finished forming. Countless asteroids and comets still populated the space between the planets, and their orbits frequently brought them into collision courses with the inner worlds. Mars, like Earth, the Moon, and Mercury, was subjected to a period of intense bombardment that lasted for several 100 million years. The largest impacts during this era created enormous basins that still dominate the Martian surface today. The most dramatic feature possibly created during this period is the Borealis Basin, also known as the Northern Lowlands. The entire northern hemisphere of Mars sits several miles lower than the southern hemisphere, a striking asymmetry called the Martian dichotomy. One hypothesis suggests that this dichotomy was created by a single, catastrophic impact early in Martian history. A body perhaps 100-200 miles across, larger than the asteroid Ceres, may have struck Mars at an oblique angle, excavating the northern hemisphere and leaving behind the largest impact basin in the solar system. If this hypothesis is correct, the Borealis impact would have released enough energy to melt much of the Martian surface and blast enormous amounts of debris into space, some of which may have contributed to the formation of Phobos and Deimos. Other scientists propose alternative explanations for the dichotomy, including differences in crustal formation during the magma ocean stage or long-term mantle convection patterns that thinned the crust in the northern hemisphere. The question remains unresolved, and understanding the origin of the Martian dichotomy is one of the major goals of ongoing research. Several other large impact basins formed during the early bombardment period. Hellas Basin, located in the southern hemisphere, is the largest clearly visible impact structure on Mars. Measuring about 1,400 miles across and more than 5 miles deep, Hellas is so large that its floor experiences atmospheric pressure nearly twice that of the surrounding highlands. The basin is often filled with dust and clouds, creating a bright spot visible through Earth-based telescopes. The impact that created Hellas would have been cataclysmic, releasing energy equivalent to billions of nuclear weapons and ejecting material that fell across the entire planet. Argyre Basin, another major impact structure in the southern hemisphere, measures about 500 miles across. Though smaller than Hellas, Argyre is still enormous by terrestrial standards, larger than any impact basin on Earth. The Isidis Basin, located on the boundary between the northern lowlands and southern highlands, is similar in size to Argyre and may have once contained a lake or sea when Mars had a thicker atmosphere and warmer climate. Scientists have divided Martian geological history into 3 major periods, named after regions on the planet that exemplify each era. The oldest period, the Noachian, lasted from the formation of Mars until approximately 3.7 billion years ago. The Noachian is named after Noachis Terra, an ancient, heavily cratered region in the southern highlands. During this period, Mars experienced the heavy bombardment that created most of its large impact basins, and conditions may have been warm and wet enough for liquid water to flow across the surface. Evidence for Noachian water activity is abundant. Valley networks, branching channel systems that resemble terrestrial river drainage patterns, are found throughout the southern highlands. These valleys appear to have been carved by persistent water flow over extended periods, suggesting that rainfall or snowmelt fed rivers that drained into lakes and seas. Clay minerals, which form through prolonged interaction between water and rock, are common in Noachian terrains. The presence of these minerals indicates that water was not just present, but stable on the surface for geologically significant periods. The source of this water and the mechanism that kept Mars warm enough for liquid water remain subjects of intense debate. The young sun was approximately 30% dimmer than it is today, which should have made early Mars even colder than the present. Yet the geological evidence clearly indicates that liquid water was present. Scientists have proposed various solutions to this paradox, including a thick carbon dioxide atmosphere that created a strong greenhouse effect, volcanic emissions of sulfur dioxide and other warming gases, or impact events that temporarily heated the atmosphere and released water from the subsurface. The Noachian period also saw intense volcanic activity. The massive volcanoes of the Tharsis region began forming during this era, though they would continue to grow throughout Martian history. Volcanic eruptions released gases that replenished the atmosphere and may have contributed to the warm, wet conditions that allowed water to flow. The heat from volcanic activity could also have melted subsurface ice, creating groundwater systems that fed springs and rivers. The end of the Noachian period, approximately 3.7 billion years ago, marked a fundamental transition in Martian history. The rate of large impacts declined as the solar system settled into a more stable configuration, and conditions on Mars began to change. The Hesperian period, which lasted from about 3.7 to 3.0 billion years ago, saw a gradual shift from the warm, wet conditions of the Noachian to the cold, dry conditions that characterize Mars today. The Hesperian period is named after Hesperia Planum, a region of volcanic plains in the southern hemisphere. During this era, volcanic activity continued, with lava flows covering vast areas and building up the Tharsis volcanoes to impressive heights. The most dramatic features of the Hesperian period, however, are the outflow channels, enormous valleys that appear to have been carved by catastrophic floods of almost unimaginable scale. These outflow channels are found primarily around the Chrysoplanitia region in the northern hemisphere. They begin abruptly at chaotic terrain, jumbled landscapes of broken blocks and collapsed ground, and extend for hundreds or thousands of miles before emptying into the northern lowlands. The channels are tens of miles wide and hundreds of feet deep, with streamlined islands and scour marks that indicate flow velocities of tens of miles per hour. The volume of water required to carve these channels would have exceeded the flow of all Earth's rivers combined, released in floods that may have lasted only weeks or months. The source of this water was likely groundwater trapped beneath the surface. During the Noachian period, water may have accumulated in vast underground aquifers, sealed beneath layers of ice and rock. Volcanic activity, impacts, or tectonic stresses could have breached these aquifers, releasing their contents in sudden catastrophic floods. The water would have flowed across the surface, carving the outflow channels, before either evaporating into the thin atmosphere or freezing and sublimating away. Some of this water may have accumulated in temporary lakes or seas in the northern lowlands, though direct evidence for such bodies of water remains elusive. The Hesperian period also saw the formation of Valles Marineris, the great canyon system that stretches across the Martian equator. Unlike the outflow channels, which were carved by flowing water, Valles Marineris appears to have formed primarily through tectonic processes. The canyon system is associated with the Tharsis Bulge, the massive volcanic province that dominates one hemisphere of Mars. As the Tharsis volcanoes grew, their weight caused the surrounding crust to flex and fracture. Valles Marineris may have begun as a series of rift valleys that opened as the crust stretched, similar to the East African rift on Earth. Over time, the walls of these rifts collapsed, widening the canyons, and water may have flowed through portions of the system, further eroding and shaping the landscape. By the end of the Hesperian period, Mars had lost most of its thick early atmosphere. Without a global magnetic field to deflect the solar wind, atmospheric gases were gradually stripped away into space. The declining atmospheric pressure meant that liquid water could no longer exist stably on the surface. Temperatures dropped, and any remaining surface water froze or sublimated. Mars was becoming the cold, dry world we see today. The Amazonian period, which began approximately 3.0 billion years ago and continues to the present, is named after Amazonis Planitia, a region of young volcanic plains in the northern hemisphere. This period has been characterized by low rates of geological activity compared to earlier eras. Volcanic eruptions have continued, but at a much reduced pace. Impact craters have accumulated slowly on Amazonian surfaces, providing a way to estimate their ages. The most significant processes shaping the Amazonian landscape have been wind erosion and deposition, the seasonal advance and retreat of polar ice caps, and occasional releases of groundwater that have carved small channels and gullies. Despite the generally quiet nature of the Amazonian period, Mars has not been entirely geologically dead. The Tharsis volcanoes show evidence of eruptions within the past few 100 million years, and some lava flows may be as young as a few million years. Whether any volcanoes on Mars remain active today is unknown, but the possibility cannot be ruled out. The detection of methane in the Martian atmosphere, which should be destroyed by ultraviolet radiation within a few centuries, suggests that some process is actively releasing this gas, and volcanic activity is one possible source. The Amazonian period has also seen significant changes in Mars's climate, driven by variations in its orbit and axial tilt. Unlike Earth, whose axial tilt is stabilized by the Moon's gravitational influence, Mars experiences large oscillations in its obliquity over millions of years. When the axial tilt is high, the poles receive more direct sunlight during summer, causing the polar ice caps to sublimate and releasing water vapor into the atmosphere. This water can be transported to lower latitudes, where it freezes out as ground ice or snow. When the axial tilt is low, the poles become colder, and ice accumulates there while being lost from lower latitudes. These cycles have redistributed water ice across the planet over geological time, creating layered deposits at the poles and buried ice at mid-latitudes. Understanding the geological history of Mars is not merely an academic exercise. The conditions that existed during the Noachian period, when liquid water was present and the climate was warmer, may have been suitable for the origin and evolution of life. If life ever arose on Mars, it most likely did so during this early era, when the planet was most Earth-like. The transition to the cold, dry conditions of the Hesperian and Amazonian periods would have posed severe challenges for any Martian life, potentially driving it underground or into protected niches where liquid water might still exist. The search for evidence of past or present life on Mars is fundamentally a search through geological time, an attempt to find traces of organisms that may have flourished billions of years ago, or that may persist in hidden refuges today. Chapter 11. The Dramatic Landscape of Mars. Now let us walk across the surface of Mars in our imagination, exploring the remarkable landscapes that make this world so fascinating. From towering volcanoes that dwarf anything on Earth to canyons that would swallow entire mountain ranges, Mars presents a geography of extremes. The forces that shaped this landscape, volcanism, impacts, wind, water and ice, have left their marks across billions of years, creating a world that is both alien and strangely familiar. We begin our journey at Olympus Mons, the largest volcano in the solar system. Rising approximately 72,000 feet above the surrounding plains, Olympus Mons stands nearly 3 times the height of Mount Everest. But height alone does not capture the immensity of this mountain. Olympus Mons is a shield volcano, built up over billions of years by countless eruptions of fluid lava that spread across the surface in thin sheets. The result is a mountain of gentle slopes, averaging only about 5 degrees, that extends for 374 miles from edge to edge. If you stood at the base of Olympus Mons, you would not see a towering peak on the horizon. The mountain is so broad that its summit would lie beyond the curve of the planet, hidden from view. The summit of Olympus Mons is crowned by a complex of overlapping calderas, collapse craters formed when magma chambers beneath the volcano emptied during eruptions. The largest of these calderas measures about 50 miles across and nearly 2 miles deep. The caldera floors are remarkably smooth, suggesting that lava lakes once filled these depressions before cooling and solidifying. The relatively few impact craters on the caldera floors indicate that volcanic activity continued until geologically recent times, perhaps within the last few 100 million years. Surrounding the base of Olympus Mons is an enormous cliff or escarpment that rises up to 4 miles above the surrounding plains in some places. This cliff formed through a combination of processes, including the collapse of the volcano's flanks and erosion by wind and possibly water. Beyond the escarpment lies a vast apron of ridged terrain, material that has slumped away from the volcano over time. The total area covered by Olympus Mons and its associated deposits is comparable to the size of France. Why did Olympus Mons grow so large? The answer lies in the differences between Mars and Earth. On Earth, volcanic hotspots like the one that created the Hawaiian Islands remain stationary while the tectonic plates move above them. This movement carries volcanoes away from their magma source, limiting their growth and creating chains of progressively older volcanic islands. Mars, however, lacks plate tectonics. Its lithosphere, the rigid outer shell of the planet, has remained stationary relative to the underlying mantle. Volcanic hotspots on Mars can continue to feed the same volcano for billions of years, allowing mountains like Olympus Mons to grow to extraordinary sizes. Olympus Mons is not alone. 3 other giant volcanoes, Ascraeus Mons, Pavonis Mons, and Arsia Mons, stand in a line to the southeast, forming the Tharsis Montes. Each of these volcanoes would be the largest on Earth if transported to our planet. They sit atop the Tharsis Bulge, a vast dome of elevated terrain that rises several miles above the mean surface level of Mars. The Tharsis Bulge represents one of the most significant geological features in the solar system, a region of intense volcanic activity that has profoundly influenced the evolution of Mars. The weight of the Tharsis Bulge has deformed the entire planet. Mars bulges outward at Tharsis and is slightly flattened on the opposite side, giving the planet a subtly asymmetric shape. The stresses created by this deformation have fractured the crust, creating vast systems of faults and grabens that radiate outward from Tharsis like cracks in a windshield. These fractures extend for thousands of miles, affecting terrain across much of the planet. One consequence of the Tharsis stresses is Valles Marineris, the Great Canyon system that stretches along the Martian equator. Valles Marineris extends for more than 2,500 miles, roughly the distance from New York to Los Angeles. The canyon system reaches widths of 125 miles in places and depths of up to 4 miles. If Valles Marineris were placed on Earth, it would stretch from the Atlantic Ocean to the Pacific, swallowing the Grand Canyon as an insignificant side tributary. Valles Marineris is not a single canyon, but a complex system of interconnected troughs, chasmata, and tributary canyons. The western end of the system begins at Noctis Labyrinthus, a chaotic maze of intersecting valleys and collapsed terrain. From there, the canyon system extends eastward through a series of parallel troughs, including Ius Chasma, Melas Chasma, and Coprates Chasma. The central portion of Valles Marineris is the widest and deepest, with multiple levels of terracing on the canyon walls that record episodes of collapse and erosion. The eastern end of the system opens into chaotic terrain that transitions into the outflow channels leading to Chrysoplanitia. The origin of Valles Marineris remains a subject of scientific investigation. The canyon system clearly formed through tectonic processes, with the crust pulling apart as the Tharsis Bulge grew. But water has also played a role in shaping the canyons. Layered sediments on the canyon floors suggest that lakes may have existed within Valles Marineris at various times in Martian history. Landslides have carved enormous alcoves into the canyon walls, and some of these landslides may have been triggered by the release of groundwater. The interplay between tectonics, water, and gravity has created one of the most spectacular landscapes in the solar system. Beyond the great volcanoes and canyons, Mars displays a remarkable diversity of terrains. The southern highlands, which cover roughly 2/3 of the planet, are ancient and heavily cratered. This terrain dates back to the Noachian period, when impacts were frequent and the surface was being constantly reshaped by falling debris. The craters of the southern highlands range from small bowl-shaped depressions to enormous basins, hundreds of miles across. Many craters have been modified by subsequent processes, their rims eroded by wind and their floors filled with sediments, lava, or ice. The northern lowlands present a striking contrast. This region, which may occupy the floor of the ancient Borealis Basin, is remarkably smooth and flat. The surface is younger than the southern highlands, with fewer visible craters, suggesting that it has been resurfaced by volcanic activity, sediment deposition, or both. Some scientists have proposed that the northern lowlands once contained a vast ocean, fed by the outflow channels that drain into the region. Evidence for this ocean remains controversial, but the possibility that Mars once had a body of water comparable in size to Earth's Arctic Ocean is tantalizing. The polar regions of Mars are among the most dynamic environments on the planet. Both poles are capped by permanent ice deposits, composed of water ice, and at the South Pole, carbon dioxide ice. These permanent caps are surrounded by seasonal caps of carbon dioxide frost that advance and retreat with the Martian seasons. During winter, temperatures at the poles drop low enough for carbon dioxide to freeze directly out of the atmosphere, creating a layer of dry ice frost that can extend to mid-latitudes. During spring, this frost sublimates back into the atmosphere, sometimes creating dramatic jets of gas that carry dark material from below the ice to the surface. The North Polar Cap is a dome of water ice roughly 600 miles across and up to 2 miles thick. The ice is layered, with alternating bands of light and dark material that record variations in climate over millions of years. These layers are exposed in steep cliffs and spiral troughs that cut into the cap, providing a visible record of Martian climate history. Scientists study these layers much as they study ice cores from Earth's polar regions, using them to reconstruct past atmospheric conditions and orbital variations. The South Polar Cap is smaller but more complex. A permanent cap of carbon dioxide ice, about 5 miles across, sits atop a much larger deposit of water ice. The South Polar region also contains extensive layered deposits similar to those at the North Pole, recording millions of years of climate variations. Strange features called spiders, radial patterns of channels carved by sublimating carbon dioxide, dot the South Polar terrain, creating landscapes unlike anything found on Earth. Between the poles and the equator, Mars displays a variety of terrains shaped by wind, ice, and occasional water. Vast fields of sand dunes march across crater floors and polar margins, driven by winds that can reach speeds of 60 miles per hour during dust storms. These dunes take forms familiar from Earth deserts, including crescent-shaped Barcan dunes, linear dunes, and complex star dunes. The sand is composed primarily of basalt, giving the dunes a dark grey colour that contrasts with the rusty hues of the surrounding terrain. Wind erosion has carved distinctive features across the Martian surface. Yardangs, streamlined ridges aligned with the prevailing wind direction, are found in many regions. Ventifacts, rocks sculpted by wind-blown sand, litter the plains explored by rovers. Dust devils, spinning columns of air that lift fine particles from the surface, have been photographed by landers and orbiters, leaving dark tracks across the landscape as they remove the thin layer of bright dust that coats the surface. The Martian surface is also marked by features that speak to the presence of subsurface ice. Polygonal patterns, similar to those found in Earth's polar regions, cover vast areas of the northern plains. These patterns form when ice-rich soil contracts and cracks during temperature cycles, creating networks of troughs that outline polygon-shaped blocks. Rampart craters, impact craters surrounded by distinctive Lobati ejector patterns, suggest that impactors struck ground containing ice or water, which fluidized the ejected material and allowed it to flow across the surface. Some of the most intriguing features on Mars are the gullies found on crater walls and cliff faces, primarily in the mid-latitudes. These gullies have alcoves at their heads, channels that wind downslope, and fan-shaped deposits at their bases, a morphology strikingly similar to gullies carved by water on Earth. When they were first discovered in images from Mars Global Surveyor, many scientists proposed that they were carved by liquid water seeping from underground aquifers. The gullies appeared geologically young, with few superimposed craters, suggesting that water might flow on Mars even today. Subsequent observations have complicated this picture. Some gullies have been observed to change over time, with new channels appearing and existing channels extending, but these changes occur during winter, when temperatures are far too cold for liquid water. Current thinking suggests that most gullies are carved by carbon dioxide frost, which accumulates on slopes during winter and then sublimates rapidly in spring, triggering flows of dry material. However, some gullies may indeed have been carved by water in the past when Mars's climate was different, and the debate continues. The diversity of Martian landscapes reflects the complex history of the planet. Volcanism, impacts, tectonics, wind, water and ice have all left their marks, creating a world of dramatic contrasts and subtle details. Each feature tells a story, a record of the processes that shaped it and the conditions that existed when it formed. Reading these stories is the work of planetary scientists who piece together the history of Mars from the clues preserved in its rocks and landforms. Chapter 12. The Search for Water on Mars. Water is the key to understanding Mars. It shaped the ancient landscape, carving valleys and filling basins. It may have provided the medium in which life could arise and evolve. And it remains present today, locked in polar ice caps and hidden beneath the surface, waiting to be discovered and perhaps someday used by human explorers. The search for water on Mars has driven much of our exploration of the planet, and the discoveries we have made have transformed our understanding of this neighbouring world. The first hints that water had played a role in Martian history came from telescopic observations in the 18th and 19th centuries. Astronomers noted that the polar caps grew and shrank with the seasons, suggesting that some volatile substance was freezing and sublimating in response to temperature changes. The white colour of the caps led most observers to conclude that they were composed of water ice similar to the ice caps of Earth. This interpretation was not universally accepted, however. Some scientists argued that the caps might be composed of frozen carbon dioxide, dry ice, which could also explain the observed seasonal changes. The debate was largely resolved by spacecraft observations in the late 20th century. The Viking orbiters measured temperatures at the North Polar Cap and found them too warm for carbon dioxide ice to be stable. The North Polar Cap must therefore be composed primarily of water ice. The South Polar Cap proved more complex, with a thin layer of carbon dioxide ice overlying a much larger deposit of water ice. The total amount of water ice at the Martian poles is substantial, equivalent to a global layer of water roughly 65 to 100 feet deep if spread evenly across the planet. But the polar caps are only part of the story. The most compelling evidence for water on Mars comes from the landforms carved by flowing liquid. The valley networks of the southern highlands, with their branching tributaries and meandering channels, closely resemble river drainage systems on Earth. These valleys appear to have formed over extended periods, with water flowing persistently across the surface and gradually eroding the underlying rock. The presence of valley networks implies that early Mars had a climate warm enough for liquid water to exist, with either rainfall or snowmelt feeding the rivers. The outflow channels tell a different story, one of sudden catastrophic flooding. These enormous valleys, found primarily around the Chryse-Planitia region, show evidence of flows far more powerful than any river on Earth. Streamlined islands, scour marks, and giant ripples indicate that water rushed through these channels at velocities of tens of miles per hour, carving the landscape in a matter of days or weeks. The source of this water was likely underground, vast aquifers that were breached by volcanic activity, impacts, or tectonic stresses. The floods would have been spectacular events, releasing more water than all of Earth's rivers combined in sudden, violent outbursts. Where did all this water go? Some of it undoubtedly escaped to space, broken apart by ultraviolet radiation, and lost as hydrogen and oxygen atoms drifted away from Mars's weak gravity. But much of it remains on the planet, hidden from view. Ground-penetrating radar aboard Mars Express and Mars Reconnaissance Orbiter has revealed vast deposits of water ice buried beneath the surface at mid-latitudes. These deposits, covered by a thin layer of dry soil, contain enough water to cover the entire planet to a depth of several feet if melted and spread evenly. The Phoenix lander provided direct confirmation of subsurface ice when it touched down near the North Pole in 2008. The lander's robotic arm dug trenches in the soil, exposing bright white material just a few inches below the surface. Over the following days, this material slowly disappeared, sublimating into the thin Martian atmosphere. Only water ice behaves this way under Martian conditions. For the first time, a spacecraft had directly observed water ice on Mars, confirming what orbital observations had suggested. The distribution of subsurface ice varies with latitude. Near the poles, ice is present just below the surface and may extend to considerable depths. At lower latitudes, ice is found at greater depths, protected from sublimation by the overlying soil. The boundary between ice-rich and ice-poor terrain shifts with Mars's orbital cycles, as changes in axial tilt cause ice to migrate between the poles and lower latitudes over millions of years. Understanding this distribution is crucial for planning future human missions, as water will be an essential resource for any long-term presence on Mars. The most exciting recent discovery concerns the possibility of liquid water on Mars today. In 2018, scientists announced that radar observations from Mars Express had detected what appeared to be a lake of liquid water beneath the South Polar ice cap. The detection was based on bright radar reflections from a region about a mile below the surface, reflections that are best explained by liquid water. The water would be kept from freezing by the pressure of the overlying ice and by dissolved salts that lower its freezing point, similar to the briny lakes found beneath glaciers on Earth. Subsequent observations have identified additional bright reflections that might indicate more subsurface lakes, though some scientists have proposed alternative explanations involving unusual geological materials. The debate continues, but the possibility that liquid water exists on Mars today has profound implications for the search for life. On Earth, wherever liquid water is found, life is found as well. If liquid water persists beneath the Martian surface, it could provide a habitat for microorganisms that have survived since the planet's warmer, wetter past. The search for water on Mars is not merely a scientific curiosity. Water is essential for any future human presence on the planet. Astronauts will need water to drink, to grow food, and to produce oxygen for breathing. Water can also be split into hydrogen and oxygen, which can be used as rocket propellant for the return journey to Earth or for further exploration. Bringing all the water needed for a Mars mission from Earth would be prohibitively expensive, so future explorers will need to extract water from the Martian environment, a process called in situ resource utilization. The subsurface ice deposits detected by orbiters and confirmed by Phoenix represent a readily accessible water source. Astronauts could excavate ice-rich soil, heat it to release the water vapor, and collect the resulting liquid. The polar ice caps contain even larger water reserves, though their remote locations and extreme cold make them less practical for early missions. The possibility of liquid water beneath the surface is intriguing, but would require drilling through a mile or more of ice and rock to access. Understanding the history of water on Mars also helps us understand the planet's potential for life. During the Noachian period, when valley networks were forming and lakes may have filled crater basins, Mars may have been as habitable as early Earth. If life arose on Mars during this period, it would have had hundreds of millions of years to evolve and spread across the planet. As conditions changed and the surface became cold and dry, life may have retreated underground, following the water to depths where liquid could still exist. The search for life on Mars is, in many ways, a search for water, past and present, and the environments it created. The question of whether life exists beyond Earth is one of the most profound that humanity has ever asked. Mars, our closest planetary neighbour with a history of liquid water, has long been considered the most likely place in our solar system to find evidence of extraterrestrial life. The search for Martian life has driven much of our exploration of the planet, from the Viking landers of the 1970s to the Perseverance rover exploring Jezero crater today. The answer to this question, whether positive or negative, will reshape our understanding of our place in the universe and the nature of life itself. The possibility of life on Mars has captivated human imagination for centuries. When astronomers first observed the seasonal darkening of certain Martian regions through their telescopes, many interpreted these changes as evidence of vegetation, perhaps vast forests or grasslands that grew during the Martian spring and withered during autumn. The canal controversy of the late 19th and early 20th centuries took this speculation even further, proposing not just life, but intelligent civilization, beings capable of engineering on a planetary scale. These romantic notions were gradually dispelled by better observations and eventually by spacecraft that revealed Mars to be a cold, dry world with a thin atmosphere inhospitable to complex life as we know it. Yet the search for life on Mars did not end with the demise of the canal theory. Instead, it became more sophisticated, shifting from the search for visible signs of life to the search for microscopic organisms or their chemical traces. The Viking missions of 1976 represented the first serious scientific attempt to detect life on another planet, and the experiments they carried remain among the most ambitious biological investigations ever conducted beyond Earth. The Viking landers each carried 3 biology experiments designed to detect metabolic activity in Martian soil. The gas exchange experiment placed soil samples in a chamber with nutrients and water vapour, then monitored for changes in the composition of gases in the chamber that might indicate biological activity. The labelled release experiment added a nutrient solution containing radioactive carbon to soil samples, then looked for radioactive carbon dioxide that would be released if organisms consumed the nutrients and respired. The pyrolytic release experiment exposed soil samples to carbon dioxide and carbon monoxide containing radioactive carbon, simulating Martian atmospheric conditions, then heated the samples to see if any organic compounds had been synthesized, as would occur if photosynthetic organisms were present. The results of these experiments were tantalizing and controversial. The labelled release experiment showed a strong positive response when nutrients were first added to the soil. Radioactive carbon dioxide was released, exactly what would be expected if microorganisms were present and metabolizing the nutrients. The response was even stronger than what would be seen with some Earth soils. For a brief, exciting moment, it seemed that Viking might have detected life on Mars. However, subsequent tests cast doubt on this interpretation. When the soil was heated to sterilize it before adding nutrients, the response was greatly reduced but not eliminated. Living organisms would have been killed by the heating, so the residual response suggested a chemical rather than biological process. The other 2 biology experiments showed no clear evidence of life. Most significantly, a 4th instrument called the Gas Chromatograph Mass Spectrometer, designed to detect organic molecules in the soil, found none at detection limits of parts per billion. The absence of organic molecules was difficult to reconcile with the presence of life, since all known organisms are built from organic compounds and leave organic residues when they die. Most scientists concluded that the Viking results were best explained by chemical reactions involving highly oxidizing compounds in the Martian soil. Ultraviolet radiation from the sun, which reaches the Martian surface unfiltered due to the thin atmosphere, could produce reactive chemicals like hydrogen peroxide and perchlorates that would break down organic molecules and produce the responses seen in the biology experiments. The surface of Mars appeared to be not just lifeless, but actively hostile to organic chemistry, a natural sterilization system that would destroy any biological material exposed to it. Gilbert Levin, the principal investigator for the labelled release experiment, disagreed with this consensus. He maintained for decades that his experiment had detected life on Mars, and that the other results could be explained by the unusual chemistry of Martian organisms or by the limitations of the other instruments. Levin pointed out that the labelled release results closely matched what would be expected from biological activity, and that no purely chemical explanation could fully account for all the observations. While most of the scientific community remained skeptical, Levin's persistence kept the question open and reminded everyone that the Viking results were not as definitive as they might seem. The discovery of extremophiles on Earth added new dimensions to the search for Martian life. Beginning in the 1970s and accelerating through subsequent decades, scientists found living organisms in environments previously thought to be completely inhospitable. Thermophils thrive in hot springs and hydrothermal vents at temperatures above the boiling point of water. Psychrophiles survive in Antarctic ice and permafrost at temperatures far below freezing. Acidophiles live in pools of sulfuric acid, while alkalophiles prefer extremely basic conditions. Halophils flourish in salt concentrations that would kill most organisms, and barophils withstand crushing pressures in the deep ocean. Perhaps most remarkably, scientists discovered organisms living miles below Earth's surface in rocks with no access to sunlight or surface nutrients. These subsurface microbes derive energy from chemical reactions between water and rock, a process that could occur on any rocky planet with liquid water. The discovery of this deep biosphere expanded the potential habitats for life enormously, suggesting that life might exist beneath the surfaces of worlds that appear barren from above. These discoveries transformed thinking about Mars. Even if the surface is inhospitable, the subsurface might provide refuges where liquid water exists, and life could survive. The detection of subsurface ice and the possibility of liquid water beneath the polar caps raised the prospect that Mars might harbour a hidden biosphere, organisms that retreated underground billions of years ago when the surface became cold and dry, and have persisted ever since in protected niches. The ALH 84001 meteorite controversy of 1996 briefly reignited hopes that evidence of Martian life had already been found. This meteorite, collected in Antarctica in 1984, was identified as originating from Mars based on the composition of gases trapped within it, which matched the Martian atmosphere as measured by Viking. The rock had been blasted off Mars by an asteroid impact millions of years ago, travelled through space, and eventually fell to Earth, where it lay on the Antarctic ice until its discovery. A team of NASA scientists led by David McKay announced that ALH8 4001 contained several features consistent with ancient biological activity. They reported finding carbonate minerals that might have been deposited by liquid water, iron sulfide and iron oxide minerals that on Earth are often produced by bacteria, organic molecules called polycyclic aromatic hydrocarbons that could be breakdown products of living organisms and tiny elongated structures that resembled fossil bacteria. Taken together, the researchers argued, these features suggested that microscopic life had existed on Mars billions of years ago. The announcement generated enormous public excitement and prompted President Bill Clinton to make a statement from the White House lawn. But the scientific community responded with skepticism. Critics pointed out that each of the purported biosignatures could be explained by non-biological processes. The carbonate minerals could have formed from volcanic fluids or impact melts. The iron minerals could have been produced by inorganic chemical reactions. The organic molecules could be contamination from Antarctic ice, or could have formed through processes unrelated to life. And the tiny structures, measuring only about 100 nanometers in length, were far smaller than any known bacteria, and might simply be mineral formations. Over the following years, the evidence for life in ALCHE 4001 was largely discounted. Most scientists concluded that the features described by Mackay and his colleagues did not require a biological explanation, and that the meteorite did not provide convincing evidence for Martian life. However, the controversy had important consequences. It focused public and scientific attention on the search for life on Mars, helped justify increased funding for Mars exploration, and stimulated research into biosignatures, the chemical and physical traces that life leaves behind. The search for life on Mars today focuses on several complementary approaches. One approach is to look for organic molecules, the carbon-based compounds that are the building blocks of life. While the Viking gas chromatograph mass spectrometer found no organics, more sensitive instruments on later missions have detected them. The Curiosity rover has found several types of organic molecules in Martian rocks, including thiophanes, benzene, and toluene. These molecules do not prove that life exists or ever existed on Mars, as they can be produced by non-biological processes and could have been delivered by meteorites. But their presence demonstrates that the raw materials for life are available on Mars, and that organic chemistry can occur despite the harsh surface conditions. Another approach is to search for environments where life could exist or could have existed in the past. The discovery of ancient lake beds, river valleys, and mineral deposits that form in water has identified numerous locations where conditions may once have been suitable for life. Jezero Crater, where the Perseverance rover is currently operating, was chosen specifically because it contains an ancient river delta, a type of environment that on Earth is particularly good at preserving organic material and microfossils. By examining the rocks of the Jezero Delta, Perseverance may find evidence of ancient Martian life, if it ever existed. The most definitive approach would be to return samples from Mars to Earth, where they could be analysed with the full power of terrestrial laboratory instruments. Perseverance is collecting and caching samples for this purpose, sealing them in tubes that will be retrieved by a future mission and brought back to Earth. The Mars Sample Return Campaign, a joint effort by NASA and the European Space Agency, aims to accomplish this feat within the next decade or so. If Martian samples contain evidence of life, whether fossil microbes, organic biomarkers, or isotopic signatures of biological processes, scientists on Earth will have the best chance of finding it. The detection of methane in the Martian atmosphere adds another intriguing element to the search for life. Methane is a simple organic molecule that on Earth is produced primarily by living organisms, particularly microbes called methanogens that thrive in oxygen-free environments. Methane can also be produced by geological processes, such as the reaction of water with certain minerals at high temperatures. The presence of methane on Mars is puzzling because the molecule should be destroyed by ultraviolet radiation within a few hundred years. Its continued presence suggests an ongoing source that replenishes the supply. Both Mars Express and the Curiosity rover have detected methane in the Martian atmosphere, though the measurements have been inconsistent and difficult to interpret. Curiosity has observed seasonal variations in methane levels, with higher concentrations in summer and lower concentrations in winter. The source of this methane remains unknown. It could be biological, produced by microorganisms living beneath the surface. It could be geological, released by volcanic activity or by reactions between water and rock. Or it could be the slow release of ancient methane trapped in subsurface ice. Determining the source of Martian methane is one of the key goals of ongoing and future exploration. The question of life on Mars is not just about whether organisms exist there today, it is also about whether life ever arose on Mars in the past, and if so, whether it shares a common origin with life on Earth. The early solar system was a violent place with frequent impacts that blasted material from one planet to another. Rocks from Mars have fallen to Earth as meteorites, and rocks from Earth have almost certainly reached Mars. If life arose on one planet early in solar system history, it could have been transported to the other, seeding both worlds with the same biological lineage. This possibility raises profound questions. If we find life on Mars and it proves to be related to Earth life, sharing the same basic biochemistry of DNA, RNA, and proteins, we will not know whether life arose independently on both worlds or whether one planet seeded the other. Only if Martian life proves to be fundamentally different from Earth life, using different genetic molecules or different metabolic pathways, will we have evidence that life can arise independently, that the universe may be full of living worlds. Conversely, if we search thoroughly and find no evidence that life ever existed on Mars, that result will also be significant. It will suggest that the origin of life is not inevitable, that even on a planet with liquid water and the right chemical ingredients, life may fail to arise. This would have implications for the search for life elsewhere in the universe, suggesting that habitable worlds may not necessarily be inhabited. The search for life on Mars continues, driven by curiosity, by the desire to understand our place in the cosmos, and by the hope that we are not alone. Each rover that trundles across the Martian surface, each orbiter that peers down from above, brings us closer to answering one of humanity's oldest questions. Whether the answer is yes or no, it will transform our understanding of life and its possibilities. Chapter 14. The Atmosphere and Climate of Mars. Let us now turn our attention to the thin veil of gases that surrounds Mars, an atmosphere so tenuous that it would be considered a vacuum by Earth standards, yet one that profoundly shapes the Martian environment. The atmosphere of Mars tells a story of dramatic change, of a world that may once have been warm and wet, but has become the cold, dry desert we see today. Understanding this atmosphere, how it formed, how it evolved, and how it behaves today, is essential to understanding Mars itself. The Martian atmosphere is composed almost entirely of carbon dioxide, which makes up about 95% of the total. The remaining 5% consists mostly of nitrogen and argon, with trace amounts of oxygen, carbon monoxide, water vapour, and other gases. This composition is strikingly different from Earth's atmosphere, which is dominated by nitrogen and oxygen, but it is similar to what Earth's atmosphere might have been like billions of years ago, before life transformed it through photosynthesis. The most striking characteristic of the Martian atmosphere is its thinness. The average surface pressure on Mars is only about 6 millibars, less than 1% of Earth's sea level pressure of 1,013 millibars. This is so low that liquid water cannot exist stably on the Martian surface. At pressures below about 6.1 millibars, water transitions directly between solid ice and gaseous vapour, skipping the liquid phase entirely. This process, called sublimation, is why the Martian polar caps shrink by evaporating directly into the atmosphere rather than melting into liquid water. The thin atmosphere has profound consequences for the Martian environment. It provides little insulation against the cold of space, allowing surface temperatures to swing wildly between day and night. Daytime temperatures near the equator can reach a relatively mild 70 degrees Fahrenheit in summer, warm enough that you might be comfortable in a light jacket if not for the unbreathable air. But as soon as the sun sets, temperatures plummet, dropping to minus 100 degrees Fahrenheit or colder by dawn. The thin atmosphere also provides little protection against ultraviolet radiation from the sun, which reaches the surface at intensities that would be lethal to most Earth organisms. Despite its thinness, the Martian atmosphere is dynamic and active. Weather patterns develop and dissipate, driven by the uneven heating of the surface by the sun. Clouds form, composed of water ice or carbon dioxide ice depending on altitude and temperature. Dust devils spin across the plains, lifting fine particles into the air and leaving dark tracks on the surface. And periodically, dust storms grow to enormous size, sometimes engulfing the entire planet in a shroud of airborne particles that can persist for months. These global dust storms are among the most dramatic phenomena in the solar system. They typically begin in the southern hemisphere during spring or summer, when the polar cap is sublimating rapidly and creating strong temperature gradients that drive powerful winds. Dust lifted by these winds absorbs sunlight, heating the atmosphere and creating more wind, which lifts more dust in a runaway feedback loop. Within weeks, the storm can spread across the entire planet, reducing visibility to near zero and blocking sunlight from reaching the surface. The 2018 global dust storm was particularly significant because it ended the Opportunity rover's mission. The rover, which had been exploring Mars for nearly 15 years, relied on solar panels for power. When the dust storm blocked sunlight, Opportunity could no longer generate enough electricity to keep its systems running or to heat itself against the cold. The rover fell silent and never responded to subsequent attempts at contact. The storm demonstrated both the power of Martian weather and the challenges it poses for exploration. The seasonal cycle of the Martian atmosphere is dominated by the exchange of carbon dioxide between the atmosphere and the polar caps. During winter in each hemisphere, temperatures at the pole drop low enough for carbon dioxide to freeze directly out of the atmosphere, forming a seasonal cap of dry ice that can extend to mid-latitudes. This process removes a significant fraction of the atmosphere, causing the surface pressure to drop by about 25% between summer and winter. During spring, the seasonal cap sublimates, returning the carbon dioxide to the atmosphere and raising the pressure again. This annual breathing of the atmosphere is visible in pressure measurements from surface landers and in observations of the polar caps from orbit. The water cycle on Mars is more subtle but equally important. Water vapour is present in the atmosphere in small amounts, varying with season and location. During summer in each hemisphere, water sublimates from the polar cap and is transported toward the opposite pole by atmospheric circulation. Some of this water freezes out as frost or snow at high latitudes, while some is absorbed by the soil or condenses as ice crystals in the atmosphere, forming clouds. The total amount of water in the Martian atmosphere at any given time is tiny, equivalent to a global layer only about 10 micrometers thick if condensed as liquid. Yet this water plays a crucial role in shaping the Martian surface and may be essential for any future human presence on the planet. Clouds on Mars come in several varieties. Water ice clouds form at high altitudes and in certain regions, particularly over the great volcanoes, where air is forced upward and cooled. These clouds are thin and wispy, resembling cirrus clouds on Earth. They are most common in the aphelion season, when Mars is farthest from the Sun and temperatures are coldest. Carbon dioxide clouds form at much higher altitudes, in the mesosphere, where temperatures drop below the freezing point of carbon dioxide. These clouds were unexpected when first discovered, as scientists had assumed the atmosphere was too thin for significant cloud formation. The atmosphere of Mars was not always so thin. Evidence from geology and geochemistry suggests that early Mars had a much denser atmosphere, perhaps thick enough to warm the surface through the greenhouse effect and allow liquid water to flow. The valley networks and lake beds of the Noachian period could not have formed under present conditions, implying that the climate was dramatically different billions of years ago. What happened to this early atmosphere? The answer lies in a combination of processes that have been stripping gases from Mars over billions of years. The most important of these is sputtering by the solar wind, the stream of charged particles that flows continuously from the Sun. On Earth, the global magnetic field deflects the solar wind, protecting the atmosphere from erosion. Mars lost its global magnetic field approximately 4 billion years ago, leaving its atmosphere exposed to the full force of the solar wind. When solar wind particles strike the upper atmosphere of Mars, they transfer energy to atmospheric molecules, sometimes giving them enough velocity to escape the planet's gravity entirely. Over billions of years, this process has removed a substantial fraction of the original atmosphere. The MAVEN orbiter, which has been studying the Martian upper atmosphere since 2014, has measured the current rate of atmospheric escape and extrapolated backward to estimate how much atmosphere has been lost. The results suggest that Mars may have lost the equivalent of several bars of atmospheric pressure, enough to have maintained warm, wet conditions on the early planet. Other processes have also contributed to atmospheric loss. Photochemical reactions in the upper atmosphere break apart molecules, producing light atoms like hydrogen that can escape thermally. Impacts by asteroids and comets can blast away portions of the atmosphere directly, and carbon dioxide can be removed from the atmosphere through chemical reactions with surface rocks, forming carbonate minerals that lock away the gas permanently. The relative importance of these different processes is still being studied, but together they explain how Mars transformed from a potentially habitable world to the cold, dry planet we see today. Understanding the evolution of the Martian atmosphere has implications beyond Mars itself. It helps us understand the factors that make a planet habitable and the processes that can destroy habitability over time. Earth has maintained a thick atmosphere and liquid water for billions of years, in part because our magnetic field protects us from the solar wind. Mars serves as a cautionary example of what can happen when that protection is lost. As we search for habitable planets around other stars, the lessons of Mars remind us that habitability is not just about distance from a star, but about the complex interplay of magnetic fields, atmospheric chemistry, and geological processes. The thin atmosphere of Mars also presents challenges and opportunities for future exploration. The low pressure makes it impossible for humans to survive on the surface without pressure suits, and the lack of oxygen means that any breathable air must be manufactured. On the other hand, the carbon dioxide atmosphere is a resource that can be exploited. Carbon dioxide can be processed to extract oxygen for breathing and can be combined with hydrogen to produce methane and water, providing fuel and other essential materials. The Perseverance rover carries an experiment called MOXIE that has demonstrated the production of oxygen from the Martian atmosphere, a crucial step toward future human missions. Chapter 15: The Radiation Environment of Mars. As we continue our exploration of the Martian environment, we must consider an invisible but ever-present hazard that will confront any future human visitors to the red planet. Radiation on Mars is far more intense than on Earth, posing significant health risks for astronauts and challenging engineers to develop protective technologies. Understanding this radiation environment is essential for planning safe and sustainable human exploration of Mars. The radiation that reaches the Martian surface comes from two primary sources. The first is galactic cosmic rays, high-energy particles that originate outside our solar system, accelerated to tremendous velocities by supernova explosions and other violent cosmic events. These particles, mostly protons and atomic nuclei, travel through interstellar space at nearly the speed of light. When they strike the atoms of a planetary atmosphere or surface, they produce showers of secondary particles that can penetrate deep into rock, soil, and living tissue. The second source is solar energetic particles, bursts of radiation released by the sun during solar flares and coronal mass ejections. These events can produce intense pulses of radiation that arrive at Mars within hours of being released from the sun. While solar energetic particle events are sporadic, occurring more frequently during periods of high solar activity, they can deliver dangerous doses of radiation in short periods, potentially causing acute radiation sickness in unprotected humans. On Earth, we are protected from both types of radiation by two shields. The first is our planet's magnetic field, which deflects charged particles away from the surface, funneling them toward the polar regions where they produce the aurora. The second is our thick atmosphere, which absorbs and scatters incoming radiation, reducing the dose that reaches the surface to levels that pose little health risk for most people. Mars lacks both of these protections. The planet lost its global magnetic field approximately 4 billion years ago, leaving it exposed to the full flux of galactic cosmic rays and solar energetic particles. The thin atmosphere provides some shielding, absorbing a portion of the incoming radiation, but far less than Earth's atmosphere. The result is a surface radiation environment roughly 2 to 3 times more intense than on the International Space Station, which orbits within Earth's protective magnetic field. The Curiosity rover carries an instrument called the Radiation Assessment Detector, or RADA, which has been measuring radiation levels on the Martian surface since 2012. The data from RAD show that an astronaut on Mars would receive an average dose of about 0.67 millisieverts per day, compared to about 0.01 millisieverts per day for a person on Earth's surface. Over the course of a typical Mars mission, which might last 2 to 3 years including travel time, an astronaut could accumulate a radiation dose several times higher than the career limits currently set by space agencies for astronauts. The health effects of this radiation exposure are a major concern. High-energy particles can damage DNA, increasing the risk of cancer and other diseases. They can also cause acute effects if the dose is high enough, including nausea, fatigue, and impaired immune function. Perhaps most concerning for long-duration missions, radiation exposure has been linked to neurological effects, including cognitive impairment and increased risk of neurodegenerative diseases. Studies in animal models have shown that exposure to heavy ions, a component of galactic cosmic rays, can cause changes in brain structure and function that might affect astronaut performance and long-term health. Protecting astronauts from radiation on Mars will require a combination of strategies. During the journey to Mars, spacecraft will need to be designed with shielding materials that can absorb or deflect incoming particles. Water, polyethylene, and other hydrogen-rich materials are effective at stopping many types of radiation and could be incorporated into spacecraft walls or used to create protected sleeping areas. Some mission concepts propose using the spacecraft's fuel or water supplies as shielding, positioning tanks around crew quarters to provide additional protection. On the Martian surface, natural features could provide shelter from radiation. Caves, lava tubes, and other underground spaces would offer excellent protection, with even a few feet of rock overhead, reducing radiation levels to near-Earth values. The discovery of lava tubes on Mars detected as chains of collapse pits on the flanks of volcanoes has generated interest in these features as potential habitation sites. Living underground would also protect astronauts from temperature extremes and dust storms, though it would require significant infrastructure to make such spaces habitable. For activities on the surface, Astronauts would need to limit their exposure time and might wear protective garments incorporating radiation-absorbing materials. Habitats could be constructed with thick walls or covered with Martian soil called regolith to provide shielding. The regolith itself is mildly radioactive due to the accumulation of secondary particles produced by cosmic ray impacts, but a sufficient thickness would still provide net protection against incoming radiation. Solar energetic particle events pose a particular challenge because they can occur with little warning and deliver high doses in short periods. Astronauts on Mars would need access to storm shelters, heavily shielded spaces where they could take refuge during solar events. Monitoring systems would track solar activity and provide alerts when dangerous events are imminent, giving crews time to reach shelter. The travel time for solar particles to reach Mars, typically several hours to a day depending on the event, provides a window for protective action. The radiation environment of Mars is one of the most significant challenges facing human exploration of the planet. It cannot be eliminated, only managed through careful planning, protective technologies, and operational procedures. The health risks are real, but not insurmountable. Astronauts who travel to Mars will accept elevated radiation exposure as part of the mission, much as early explorers accepted the risks of their journeys into unknown territories. The knowledge gained and the doors opened by human presence on Mars may well justify those risks, but they must be understood and minimized to the greatest extent possible.